के गुरुजन सर्वोपरि सरस्वती के समुपासक छात्र छात्राओं को यथोचित हार्दिक अभिनंदन एवं हार्दिक स्वागत मैं करता हूँ। सभी मनुष्य जन्म से लेकर मृत्यु तक कर्म करते हैं। सभी मनुष्य सुख की प्राप्ति के लिए लालायित रहते हैं। शुभ कर्म के साथ साथ अशुभ कर्म भी जाने या अनजाने हो जाता है। प्रत्येक मनुष्य को उस कर्म का फल भोग करना पड़ता है। जैसे कि नारदी पुराण में कहा गया है, अवश्य में भोग करते पुनः पुण्य कर्म भोग करने के बाद
हाँ বলছি আপনাদের ইউটিউব লাইভটা স্টার্ট হয়ে গেছে, ঠিক আছে? আমি ডট 11টায় খুলবো।
गीता कहती है पिछले पुण्य मर्त्य लोकन में गोस्वामी तुलसीदास ने भी कहा है कि कर्म प्रधान विश्व परिराखा जो जस करहि सो तस फल चाहे। अर्थात मनुष्य को अपने कर्म का फल तो भोग करना ही पड़ता है। तो अब यहाँ प्रश्न आता है कि इस कर्म फल से मुक्ति कैसे हो सकती है? तो हम लोगों को हमेशा अच्छा कर्म करना है, जो सदाचार की नीति बताई गई है उसका पालन करना है। कोरोना का एक बहुत ही खराब समय चल रहा है, महामारी
ना कैसी
लेफ्ट হয়ে হ্যাঁ সবাইকে গুড মর্নিং গুড মর্নিং হ্যাঁ
এই এখন এসে গুড মর্নিং জানাচ্ছে মিটিংয়ে
ঠিক
গিয়ে
আছে অল দি বেস্ট
থ্যাংক ইউ।
আমাদের রিসোর্স পার্সনরা এসেছেন নাকি
ব্যাস
দুজন এসছেন আর একজন ওয়েট করছি, দুজন চলে এসছেন। শ্রীনাথ বাবু গুড মর্নিং।
या गुड मॉर्निंग सर
लाइव इज स्टार्ट है। হ্যালো,
বলছি এতক্ষণ ধরে আপনাদের গুড মর্নিং জানালেন না এটা লাইভ হচ্ছে সবাই শুনছে না এটাই স্টার্ট করেছেন আমি বললাম যে
জয়েন করছে সবাই এখন।
বাবা এখন যে আপনার লাইভ হয়ে গেছে 11টায় লাইভ করতে বলছেন আপনার ইউটিউবটা ফলো করেছেন
am I audible professor
ফলো করছি আমরা। यस सर, यू आर ऑडिबल।
এক কাজ করুন
okay
এখানে
thank
লিখে লিখে করে দেবেন এটাই
ঠিক আছে, চলতে থাকুক না, চলতে থাকুক না। প্রিন্সিপাল স্যার জয়েন করুন এখন।
ঠিক আছে না অ্যাকচুয়ালি ব্রডকাস্ট হচ্ছে তো এটাই হচ্ছে ব্যাপার নাহলে তো সেটা কম্পিউটার আমাদের
হুম 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 হুম, ঠিক আছে।
এই সুমন কি বলছিল কোথায় গেল কোথায় গেল আসতে বলেছে দাঁড়া কোথায় আছিস সুমন তো এখানে ঘুরঘুর করছে এই বাড়িতে এসেছি 10 দিন আগে ফোনটা করে আসবি
गुड मॉर्निंग सर, रिजुल सर गुड मॉर्निंग।
गुड मॉर्निंग কখন স্টার্ট করবে
আপনার জন্য ওয়েট করছি, স্টার্ট এবার করে দেবো।
আচ্ছা
আর বিসি স্যার জয়েন করলে আমরা স্টার্ট করে দেবো, সবাই চলে এসছে মোটামুটি।
আচ্ছা 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 দাঁড়ান দিদি স্যারের সাথে কথা বলি
হ্যাঁ
হ্যাঁ আমি
ওকে
আমি ফোনে কথা ওকে কথা বলি
তো ফোনে আয় না
হ্যাঁ স্যার।
হ্যাঁ, দিদি স্যারকে তো ফোনে পাচ্ছি না, তো আমরা কি স্টার্ট করে দেবে? তা উনি যখন ঢুকবেন তখন আবার ওনাকে নিয়ে নাকি কি করবে?
পার্থ? হ্যাঁ স্যার, তাহলে উনি যখন আসবেন তাহলে তখন ওনাকে আমরা add করে দেবো।
হ্যাঁ হ্যাঁ, আমি সকালে ফোন করে বলেছি, বললাম 11টায় ঢুকবো।
আচ্ছা
উনি যখন এখনো ঢুকছেন না, তার মানে আসলে আজকে হিন্দি ডিপার্টমেন্টের একটা সেমিনার আছে 11টা, বুঝলেন তো, ওদের ইউনিভার্সিটি, ওনাদের ইউনিভার্সিটি।
আচ্ছা
তো তো এবারে দেখো কি করবে, তুমি যদি সেরকম হয় তাহলে 2-1 মিনিট দেখে স্টার্ট করে দাও। হ্যাঁ, 2-1 মিনিট দেখে দাও, 2-1 মিনিট 1-2 মিনিট দেখে স্টার্ট করে দাও।
আচ্ছা আচ্ছা
ঠিক আছে।
হুম।
হ্যাঁ, এখানে বলছি না, ওখানে বলছি কবে? কালকে 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 তো একটা আছে না, এখানে বলছি না, কোথায়?
হচ্ছে কি সব করে নে।
কানে শুনে আমি তো ওইটাই করতে পারছি না, বুঝতে পারছি না। ওগুলো পড়ে পড়ে আমি কিছু বুঝতে পারছি না, ইংলিশ পড়ে বুঝতে হয়, ইংলিশ শুধু পড়ে বুঝতে হয়। আমি একবার চোখ বলাবো, আমার যে ডোমেনের ইংলিশ, আমি চোখ বলাবো ভুলে যাবো। একটা ডকুমেন্ট আছে, একটা একটা ডকুমেন্ট আছে, হ্যাঁ শোন আমি শোন, এটা প্রত্যেক তুই তোদের নয়, প্রত্যেকটা প্রজেক্টেরই একটা ডকুমেন্টেশন হয়, একটা ফেজ হয়, ফার্স্ট ফেজ, সেকেন্ড ফেজ, থার্ড, সেই অনুযায়ী টাকা পেমেন্ট হয়। আমি ওটা করছি না, আমাদের সেটা হয়, ওই সেইগুলো ডকুমেন্টেশন, ফার্স্ট হচ্ছে ডকুমেন্টেশন পাঠালো, করে আমাদের ডেভেলপ করলো, পাঠালো, এটা করছি না আমি। আমি যে ডকুমেন্টটা বানাচ্ছি একটা প্রসিডিওর, কমিশনিং প্রসিডিওর, তুই যদি কমিশনিং করেছিস প্রসিডিওরটা লেখা আছে। এবার এখানে অন্য একটা পুরোপুরি লেখা আছে, সেখান থেকে আমি এডিট করছি। তো আমাকে প্রত্যেকটা লাইন তো পড়তে হবে, পড়ে পড়ে আসতে হবে, তো আমার সেটা সেই স্ক্রিপ্টে বানানো হচ্ছে, তার এনআইডি আলাদা, তার বেসিক ইঞ্জিনিয়ারিং আলাদা, বেসিক ডিজাইন আলাদা, সেটা সবাই ঠিক কী হয়? পড়তে হবে না, না পড়ে দিবি আমি এরকম 128টা পেজ ডকুমেন্ট, আমার কাছে আছে 100 পেজ একটু বেশি থাকতে হবে, 100 থাকলে 1000 এক্সপিরিয়েন্স আমার এখানে, এরকম একটু এরকম করলে আরও ভালো লাগে। ভালো করা যায় না, এটা তো টেকনিক্যাল না, এখানে টেকনিক্যাল না, অর্ধেকটাই টেকনিক্যালি বলে, সুযোগটা কি প্রবলেমগুলো বোঝা, জানা যায়, এখানে গ্রামারও দেখ খুব সোজা হয়ে যাবে, হ্যাঁ এখানে বিচার করতে হয়ে যাবে, ওখানে কি টোটাল টাইম ডাইনামিক, কি প্রবলেম খুঁজে বার করো, কম্পিউটারটাও তাই, প্রফেশনের কোনো প্রবলেম বলে আসবে না, এটাই প্রবলেম, এই প্রবলেম।
স্যার, পিন্টু স্যার, আমরা কি শুরু করতে পারি তাহলে?
না বসে থাকো,
হ্যাঁ, লেটেস্ট স্টার্ট।
প্রবীর, প্রবীর স্টার্ট। সুভাষ বাবু, আমরা স্টার্ট করছি, জানি না একবার সুভাষ বাবু।
জয়বাবু এসছেন, জয়েন করেছেন?
হ্যাঁ, সুভাষ বাবু আসছেন, সুভাষ দত্ত, টেকনিক্যাল অ্যাসিস্ট্যান্ট।
ঠিক আছে, লেটেস্ট
প্রবীর, প্রবীর, প্রবীর স্যার ফোনে ফোনে আছে।
হ্যাঁ, আমি স্টার্ট করে দিচ্ছি তাহলে। হ্যাঁ
হ্যাঁ হ্যাঁ হ্যাঁ।
Good morning, ladies and gentlemen. The honorable dignitaries, eminent resource persons, invited guests, teachers, students, the audience in the different part of the world, and my colleagues. I am Probir Sen on behalf of Mathematics Department. Welcome you all to the one-day national webinar on current studies of applied mathematics.
privilege for us that the department of organized a national webinar on the topic Current Studies of Applied Mathematics. The topic, which is very much interesting and relevant in the present scenario. I have a great proud privilege to welcome Professor Dr. Sadhan Chakraborty, Honorable Vice Chancellor, Kazi Nazrul University, Asansol, for giving his consent to act as an innovator of this webinar, in spite of his busy academic schedule. It's my great pleasure to welcome Dr. Sandeep Samanto, Assistant Professor, Department of Mathematics, Bankura University, West Bengal, for giving his presence at this beautiful seminar. It's my great pleasure to welcome Professor Subhasis Chatterjee, Professor, Department of Applied Mathematics, Indian School of Mines, Dhanbad, Jharkhand, for his towering presence at this webinar. A warm welcome to Dr. Snehashish Kundu, Assistant Professor, Department of Mathematics, NIT, Jamshedpur, Jharkhand. I take the opportunity to welcome to all the participants like teachers, scholars, students and other dignitaries present in this webinar. I hope and believe that this webinar will succeed with all its objectives. I'm sure this seminar will be a rewarding venture for all of us present here. Before I end, I again welcome all the resource persons and all other dignitaries, speakers and others present here. Thank you.
Okay. Sir. Hello. Thank you so much, sir. Thanks a lot for your valuable words. Dr. Sadhan Chakraborty, our honorable VC, is not present here, so we can start our technical session, sir. Over to you, Prakash. Good morning, everybody. I am Prakash Kumar Das. Warmly welcome you all to this beautiful program. On behalf of Mathematics Department, I am going to start the technical session of the webinar. The viewers are free to ask any questions to our speakers by typing them in the chat box of YouTube Live and Google Meet. My colleague Mr. Parthamondal shall note it down and ask your doubts to our speakers at the end of their presentation. It is now my great pleasure. It is my great pleasure to introduce our first speaker, Dr. Sudeep Samanto, Assistant Professor, Department of Mathematics, Bankura University. Dr. Samanto got his BSc and MSc degree from Jadavpur University. He received his PhD in Applied Mathematics from the Calcutta University. He was also a visiting scientist of Indian Statistical Institute, Kolkata, and University of Warsaw, Poland. He also worked as assistant professor of King Abdulaziz University, Saudi Arabia, 2017 to 2019. He has published more than 50 research articles in International Journal of Repute. Currently, 3 students pursuing their PhD under his guidance. Now, I request Dr. Samanto to deliver his talk. Dr. Samanto, from here, over to you, sir.
Okay. Thank you, Dr. Das, for introducing me. Very good morning to all. Before I start, I would like to thank the organizer for inviting me to deliver my speech on the webinar Current Studies of Applied Mathematics. I hope most of the audience are from undergraduate students. That's why I choose a very simple topic which connects undergraduate level knowledge with some basic applied mathematics research and in particularly mathematical biology or complex dynamics. Okay, let me share my PPT. Sorry, it is not shared.
ক্যামেরাগুলো ঘুরে যাচ্ছে না চ্যাট করছি কোনো বলতো না হ্যাঁ
Okay, is it visible?
Yes, visible. Yes, screen is visible, sir.
PPT is visible or not?
No.
Okay, let me share again. Okay. Okay.
Yes, sir. It is visible now.
Okay. Thank you. Title of my talk is Predicting Love Life of a Couple from Love Affairs Model. Before coming into the modeling part, I would like to briefly discuss about the basic mathematics is used for analysis of those model and modeling purpose and analysis. The content of talk is prerequisite mathematics, that is system of linear differential equation and how we can solve them, solution and stability analysis. Then we will construct step by step the mathematical models on love affair. We choose 3 different cases. First one is star-crossed romance, then identically cautious lovers and love triangle. Then we will conclude. First, how system of linear differential looks like. Here, nth order linear system of differential equation with constant coefficients is given. Here, dx1 dt is equal to a11 x1 plus a12 x2 and so on. Here, all xi's are the dependent variable and t is the independent variable. ai's, ij are the constant coefficient and fi is a function of t. Now, this system of differential equation can be written in the matrix form, that is x dot is equal to ax plus ft. Here a is the coefficient matrix and ft is the vector function with component f1 f2 dot dot fn, and x is the vector function where x1 x2 dot dot xn are component. Now if the vector function ft becomes 0, identically 0, then the system becomes homogeneous, and we use this homogeneous equation for modeling purpose here. Now, how to solve this basic system of linear homogeneous equation? There are several methods. We can reduce or eliminate variable and reduce into a single equation. However, it will be higher order equation and we can solve them. And another method is eigenanalysis method, that is matrix method. Here we will use that method. For that, we need to calculate the eigenvalues of the coefficient matrix and the eigenvector corresponding to those eigenvalues. Here we consider a two-dimensional model with two variables x1 and x2. This equation is given dx1 dt is equal to a11 x1 plus a12 x2 and dx2 dt is equal to a21 x1 plus a22 x2. It can be represented as matrix form. Dx dt is equal to ax. A is the coefficient matrix and x is the vector function with component x1 and x2. Now we need to calculate for analysis, we need to calculate the eigenvalues. However, if the eigenvalues are distinct, then how we find the solution? Let lambda 1 and lambda 2 are the eigenvalues of the coefficient matrix, and alpha 1 and alpha 2 be the eigenvector of the coefficient matrix corresponding to the eigenvalues lambda 1 and lambda 2. Then the solution of the system can be written as xt is equal to c1 into alpha 1 into e to the power lambda 1 t plus c2 into alpha 2 into e to the power lambda 2 t, where c1 and c2 are arbitrary constant. Now we will discuss the situation when eigenvalues repeats. Let us consider that the coefficient matrix has lambda 1 eigenvalues with multiplicity 2, and alpha be the eigenvector corresponding to the eigenvalue lambda. Then to find the solution, we need another vector or eigenvector which will be independent to this alpha. From the equation a minus lambda I into beta is equal to alpha, we can find that vector. Here, interestingly, this beta vector is not unique. However, it must be independent to alpha. Then alpha into e to the power lambda t and alpha t plus beta into e to the power lambda t, these two vector function will be solution of the system, and these solutions are independent. Then the general solution can be written as xt is equal to c1 alpha e to the power lambda t plus c2 into alpha t plus beta e to the power lambda t. Here c1 and c2 are arbitrary constants. Now I will discuss some basic example of these two cases. Here we consider a system with coefficient matrix 6 minus 3 to 1, this system of equation. For this coefficient matrix, we obtain two eigenvalues, lambda 1 is equal to 3 and lambda 2 is equal to 4. And the eigenvector corresponding to lambda is equal to 3 is alpha 1, that is 1 1 eigenvector, and eigenvector corresponding to eigenvalue 4 is 3 2. Then the general solution can be written as c1 into x1t and x2t is equal to c1 into this vector into e to the power lambda, that is 3t, plus c2 into second eigenvector into e to the power lambda 2t. With initial value x1 at 0 is equal to 5 and x2 at 0 is equal to 1, we compute the solution and draw them. Here the blue curve is given for x1 component and red curve is given for x2 component. Similarly, we discuss an example where eigenvalue repeats. Here, for this system of equation, x dot is equal to 4 minus 1, 1, 2 into x. The coefficient matrix is 4 minus 1, 1, 2. Here, we can simply calculate the eigenvalue, and we can observe that lambda is equal to 3, the eigenvalue is repeats, that is, it occurs with multiplicity 2. The eigenvector corresponding to lambda is equal to 3 is alpha is equal to 1 1 eigenvector. Therefore, we need another eigenvector which will be independent to alpha. From the equation a minus lambda I into beta is equal to alpha, we can compute beta is equal to 1 0, and the corresponding solution, general solution, will be looks like this. In red color we have written here c1 into first eigenvector into e to the power lambda t plus c2 into first eigenvector into t plus second eigenvector into whole into e to the power 3t. Now I would like to discuss about the stability analysis of the equilibrium point. For the linear system of equation, system of differential equation, there is 0 0 equilibrium, only one equilibrium which is trivial. This theorem deals with the stability of that equilibrium point. If we consider the system dx dt is equal to ax with initial value x at 0 is equal to x0 with coefficient matrix A and x is the vector function where component are x and y, then the equilibrium point will be asymptotically stable if and only if all the eigenvalues have negative real part. That is, for all eigenvalues, real part of lambda I less than 0. Now, there are several cases. For two-dimensional case, there are several situations when eigenvalues will be positive, negative, or imaginary. Depending on this, we first calculate the characteristic equation of the coefficient matrix, and we can write them this as lambda square minus trace A into lambda plus determinant of A. Depending on the sign or value of trace of the coefficient matrix and determinant of the coefficient matrix, we can get different situation or different values of eigenvalues. Here, for determinant negative, there will be always one negative eigenvalue, and in that case, equilibrium point will be settled. In above, that is for determinant greater than 0, there will be two situations, trace less than 0 and trace greater than 0. For trace less than 0, all the eigenvalues will be negative or will have negative real part. In this parabolic region is given by the discriminant. When discriminant is 0, that's this parabolic curve. Inside this parabolic curve, all the eigenvalues are imaginary. However, in this region, in left hand side, the imaginary values will have negative real part. Then the equilibrium point will be stable focus. It will be spiral inward. And in the outside this parabolic region, all the eigenvalues will be negative. That is why the equilibrium point will be stable node. And in first quadrant, we observe inside this parabolic curve, eigenvalues are eigenvalues are imaginary with real part is greater than 0. That's why here equilibrium point will be unstable and the solution trajectory will diverge and spiral outward. However, in y-axis, here trace is equal to 0. In this situation, all the eigenvalue will be purely imaginary and the equilibrium point will be a center. And center means all the solution trajectory will produce closed orbit passing through the initial point. Now, depending on the eigenvalues, we draw the all possible dynamics of a two-dimensional system. Here, if the eigenvalues are negative and they are equal, then all the solution trajectories converges to 0, 0 in a straight line from any initial point. However, if the eigenvalues are negative, however, they are different. Here, negative means all are real negative, and they converge to 0, 0 point along this curve. For imaginary eigenvalue, if the real part are negative, here alpha is greater than 0 is considered. That's why real part will be negative. In that case, the equilibrium point will be stable focus and solution trajectory will form spiral inward. And for real part greater than 0 for complex eigenvalues, the solution will be spiral outward. It will be unstable focus. Again, for lambda 1, lambda 2 is equal to alpha, which is greater than 0, then all the solution diverges from the equilibrium point and it follows straight line, diverges along straight line. However, if the eigenvalues are positive, however they are different, that is distinct, then solution diverges along the curved path. And when system produces purely imaginary eigenvalue, then the equilibrium point becomes center and it produces closed orbit. If I choose any initial point, then it will complete a closed curve, any equilibrium point. And for the last case, when two eigenvalues are with opposite sign, first eigenvalue is negative and second is positive, it will be vice versa. Then in that case, the equilibrium point will be saddle. Saddle means from one side it is attracting and from another side it is repelling. That's why it tries to close to the 0 point from this axis, and from this axis it is repelling, diverges. For all the quadrant it is true. Now we will formulate, based on this basic knowledge, we will formulate the love affair model. For love affair model, we choose the famous love story Romeo and Juliet. The famous love story Romeo and Juliet was written by William Shakespeare in 1599. Here, the two persons, Romeo, we consider Romeo and Juliet are in love. Here, two persons, however, we formulate the variable, that is feelings. They are feelings for each other. Here, RT be the Romeo's love or hate for Juliet, and JT be Juliet's love or hate for Romeo at time t. Positive values of R and J signify love, and negative values signify hate. The simple love affair model can be written as R dot is equal to AR plus BJ and J dot is equal to CR plus DJ, where A, B, C, D, these all parameters either be positive or negative depending on the situation. This model was proposed by Strogatz in 1988. This is very simple model. However, this simple model can produce very rich dynamics. We will study them step by step. First, we consider the case star-crossed romance. The star-crossed romance describes a pair of lovers whose relationship is prevented by outside force. It is believed that their relationship is prevented by the evil star. Those believe in the star effect. However, we consider that Romeo is in love with Juliet, but Juliet is fickle lover. That means she is very whimsical and moody. The more Romeo loves her, the more Juliet wants to run away and hide. But when Romeo gets discouraged and backs off, Juliet begins to find him strangely attractive. On the other hand, Romeo tends to echo her when he warms up, when she loves him, and he grows cold when she hates him. That means he reciprocates his, things. Here, star-crossed romance can be modeled as see that R dot is equal to AJ. That means R itself not involved. However, for Juliet feelings, it reciprocate. And again, Juliet's feelings is described by this equation minus BR. That means if Romeo shows love or affection, Juliet reacts negatively. That's why minus B is considered. Now we will check the analysis, what will happen in long run. Here 0, 0 is the equilibrium point, and the coefficient matrix, that is Jacobian matrix, is 0A minus B 0. Here the characteristic equation is lambda square plus AB is equal to 0, that is eigenvalues are lambda 1 2 is equal to plus minus I root AB, purely imaginary. Therefore, the equilibrium point will be a center. And we draw this picture. Here in first quadrant, see that all the values are positive. That means Romeo and Juliet loves each other. In second quadrant, Romeo hates Juliet. However, Juliet loves Romeo. In third quadrant, we observe that all values are negative. That means both of them are fighting or hate each other. However, in fourth quadrant, Romeo loves Juliet. However, Juliet hates Romeo. So there is a cycle, never-ending cycle of love and hate. Results: the equilibrium point is a center, and the sad outcome is that there is a never-ending cycle of love and hate. The positive side is that at least 1/4 of time they love each other simultaneously. Only 1/4 of time. Okay, next case, we consider two identically cautious lovers. What is cautious lover? I will discuss after this model. For identically cautious lover, their love affairs can be written as R dot is equal to AR plus BJ and J dot is equal to BR plus AJ. Here A is negative and B is positive. Here alpha is the measure of cautiousness. That is, they try to avoid throwing themselves at other, and B is the measure of responsiveness. That is, they both excited by the other's love or affection. That's mean here, see, R dot is equal to AR. That's mean his own feelings increasing the feeling involvement in the relationship. And BJ means for Juliet feelings, what is the reaction of Romeo or for his response. Similarly, in this is BR, that means Juliet's response for Romeo feelings, and AJ means her own feelings or involvement in the relationship. In cautious case, these own feelings are always negative. That is, A is negative, and they will only respond when his or her partner show love or affection. Now, in that case, we analyze the equilibrium point. Equilibrium point is 0, 0, and Jacobian matrix is A, B, B, A. Then the characteristic equation is lambda square minus 2a lambda plus a square minus b square is equal to 0. Therefore, we find two eigenvalues a plus minus b. The eigenvector corresponding to the eigenvalue a plus b is 1, 1, and the eigenvector corresponding to the second eigenvalue a minus b is v2 is equal to 1 minus 1. Now, we check two cases when a square greater than b square. That means absolute value of a. Here a is negative already we told in the, during the modeling part. Is absolute value of a greater than the absolute value of b. In that case, the system is so stable node. That is, equilibrium point will be stable. Whatever be the initial point, all solution converges to 0, 0. And here it is clear from the eigenvalue also, all the eigenvalues are negative. That means whatever their initial feelings, after long run, there will be 0, 0. That means there will be no feelings or interest for each other. No love, no hate. They will be indifferent. And in the case a square less than b square, that is, cautiousness is less than the response. In that case, one eigenvalue, first eigenvalue a plus b will be positive, and second eigenvalue a minus b will be negative. In that case, we see that if the initial values are above the line along the vector v2, above that, all solution goes toward positive infinity or positive in first quadrant along the v1 vector. That means they will be love forever. However, if the initial values are from the left hand side or below this straight line, then all goes to the negative. Both values will be negative, and they will be in fight forever. They will hate each other. The result for a square greater than b square, the equilibrium point is stable node. The physical meaning is that there the relationship always ends quickly after hopeful beginning. That's when any initial value, they will converge to 0, 0. In long run, that is, for excessive caution can lead to apathy, no interest for each other. And in second case, a square less than b square, then the fixed point 0, 0 will be saddle point. Then depending on their okay, in that case, lovers are more daring or perhaps more sensitive to each other. Their relationship is explosive. Depending on their initial value, they become in love-fest or war. In all the cases, in the last figure, all the cases, the solution goes along the line R is equal to J. It will be positively or negatively. So two cases. They will be in love or war. Now, we will discuss a third case, love triangle. And in this case, we use nonlinear model, not linear. Here, we consider that Romeo and Juliet are in love. However, Romeo has an affair, that is extramarital affair with Georgia. In that case, we consider the feelings for each other. RJ is Romeo's feelings or hate for Juliet, and JB the Juliet's feelings, that is love or hate for Romeo. RG be the Romeo's feelings for Georgia, and G be the Romeo's love or hate for Georgia's love or hate for Romeo. The positive values indicates love and negative values indicate hate. Then the nonlinear love triangle model can be written as this. Here, in the previous ARJ was present, but here this term is considered logistic equation to introduce nonlinearity. That means Romeo's feelings for Juliet depends A into RJ plus B into this logistic equation. Similarly, for Juliet's feelings for Romeo is governed by this logistic equation, and DJ means her own feelings, and here MJG is considered. That means there is a competition between Juliet and Georgia. Again, RG means Romeo's feelings for Georgia is governed by this equation, A into RG plus B into this logistic equation. That is, this logistic equation are function of J minus D. That means their love feeling, difference between their love feelings. And here G minus J is considered in third equation. And the fourth equation is Georgia's feelings for Romeo is governed by, again, the logistic equation, E into that logistic equation, plus FG. G means FG means her own feelings, and minus NJG. Here J into G indicates again the competition term. Now, we did not mathematically solve this. Actually, nonlinear function, this type of cannot be exactly solved. However, we can do stability analysis. Here I also ignore the stability analysis, only discuss the simulation part. Using Rangagutta 4 method, we can easily solve. Even other numerical technique, we can solve this situation. Here, check this model once again, because these values are very important. Here we consider that Romeo and Georgia are cautious lover. That means for their own feelings is negative. They are not involved at all. But however, this B will be positive. This B will be positive. That means from others' feelings, they will be encouraged and involved in the relationship. Check. We consider Romeo and Georgia are cautious lover. That means A is negative and B is positive. Therefore, Georgia F is negative and E is positive. Others' involvement, this B, and others' involvement, and make them excited and involve them in the relationship. However, Juliet is narcissistic nerd. That means she is very much self-involved or whimsical. In that case, for her feelings for others is negative and her own feelings is positive. We consider these parameter values, and we also choose the competition coefficients as 0.1 and 0.2, each other competing 0.1. Then we solve this, simulate this system and observe stable dynamics for these system, parameter values. This phase portrait is drawn in RJ and J plane. That means Romeo's feelings for Juliet and Juliet's feelings for Romeo. We observe that this 0,0 equilibrium point is stable. That means for this situation or this type of parameter values, the system will be stable at 0,0. That means 4 component. All will be apathetic. There will be no hate or no love. They lost interest in long run. However, for if this Juliet's involvement increased, self-involvement increased, if we choose D is equal to 2, then the system shows chaotic dynamics. Here, again we draw the face portrait for this t is equal to 2, and we observe a strange attractor. This is chaotic dynamics. Next, we draw the time series solution of Romeo's feelings for Juliet, and in x-axis this is t, and here y-axis Romeo's feelings for Juliet. We observe these time series evaluations are aperiodic or irregular, or in short, they are chaotic. However, we draw two solutions in blue color and red color by changing very small initial condition, and observe that for very small time the solution are very close or similar. However, after a time point, this solution diverges. This indicates the sensitivity of the system with initial condition. Conclusion. We observe that two-dimensional linear love affair model shows various types of dynamics such as stable node, saddle node, center, depending on their individual behavior or characteristic of Romeo and Juliet. However, in nonlinear love triangle model, if a third party or third person enters into the Romeo-Juliet system, then it can produce chaos and the system becomes unpredictable. This is my conclusion. And these are some important results. References. These first three are famous books. This is for ordinary differential equation, and these two books for nonlinear dynamics, Barco and Stroger. And last three references are on a research article on love affairs. Thank you all. Thank you for kind listening. If you have any question, please ask me. I will try to explain them.
I thank Dr. Samanto for giving such a valuable and inspirational presentation. It enlightened our knowledge on the topic, especially topic on love affairs model. We have no idea in this type of model, so very, very much thank you to Dr. Samanto for giving such a valuable talk. I have some queries from the participant side. May I ask you, sir?
Yes, please.
One of our students, Rishita Das, asks, what is stress? So,
What?
sir, what is stress?
Phase.
Stress. TRS, stress.
Sorry?
Hello.
Sorry, what is? Sorry, what is?
Trace. TRACE. Trace of Hello. What is TRACE? Trace in determinant.
What is trace? Trace.
Okay.
Trace is. Okay, now I understand.
Okay.
Please. What is trace? Trace is the diagonal sum of diagonal element of the coefficient matrix. This trace of matrix, sum of diagonal element.
Okay, thank you, sir. One of our students asked this. Another question is from Mohammad Azmal Khan. He wants to ask, you take the relation R equal to AJ plus this model. So he wants to ask, what is AJ and how it interpret with this model?
Which model? First model or
first model?
First model. Okay. The first model is R dot is equal to AJ, means for R component it's have no value, don't have any R component involved here. AJ, that means it reciprocates Juliet's affection or Juliet's feelings only. These Romeo's feelings for Juliet dependent totally on Juliet's feelings for him. He has no internal, his own feelings is zero here. Okay, he only reciprocates Juliet's feelings. If Juliet hates him, then he hates Juliet, or if Juliet loves him, then he will love her. However, Juliet reacts negatively if Juliet shows Romeo shows love, then Juliet avoid him, ignore him. That's why it is negative.
Okay. Thank you, sir.
Thank you.
Sir, once again, thank you much for your input. Now, I request you to continue. Thank you.
Okay, thank you, Partho. We are greatly honored to have Dr. Subhasis Chatterjee, Professor, Department of Applied Mathematics, Indian School of Mines, Dhanbad, as the second speaker of today's webinar. Dr. Chatterjee completed his BSc in Mathematics Honours from T.D.B College under University of Vadhavan. He has done his MSc in Mathematics and PhD in Soft Reliability, both from IIT Kharagpur. He has published more than 50 research articles in international journals of repute. Under his guidance, 7 students got PhD degree and 5 are pursuing. He conducted 2 short-term courses and 1 workshop. He completed 2 major research projects funded by UGC and 1 is going on, which is funded by ISRO. He played the role of reviewer for more than 10 journals. Right now, he is serving as Associate Dean Faculty of Recruitment in the institute. He has 20 years teaching and 25 years research experience. We are so lucky that we have such a talented and famous alumni as the speaker of today's program. Your talk will inspire our students and give us the motivation to get success in career. Now, I request you, sir, to give your valuable talk.
Good morning, everybody. Am I audible to all of you?
Yes, sir, you are audible.
Okay. So already, it's really today. It's really it's a great pleasure to me that I am in front of some faculties and students who are involved with my alma mater, that Ranigans T.D.B College, T.D.B College, where I spent my 3 years of career as a student in mathematics honors studied, and I passed out from there in the 1987. So long back. Okay. So that time I was also a student like this, and there was a dream that I have to do something, some good career I have to develop. Is it okay?
Yes, sir. You are.
So with that dream, when I joined, people told me maths is very difficult. Why you have taken honors? And I told, okay, let me see. That is the only thing I understand. So so I started like that. My journey started like that, and then obviously I am very much fortunate that got a chance in a masters in Kharagpur, and then got a lot of exposure about the latest areas of research in the areas of mathematics where we can do so the research. So that gave me interest to research in the areas of theoretical computer science. So I switched over from mathematics to theoretical computer science. My main area of research is software engineering. There I did a lot of work in the areas of software reliability modeling, and that is testing phase and this your different phases of software development part that we did there. And now I am also parallelly working in the bioinformatics area also. That is main job is to develop some algorithms, clustering algorithms, classification algorithms, feature extraction. Those things we are doing at present. With me, many scholars are also there. So really, it is a great pleasure to me to today to share something with all my junior students and some learned faculties. There are just now one professor has presented his topic, and another one will present after me. Both of them are the student of T.D.B College, and I think they are junior than me. So my juniors, I can again tell. That is the thing. So now let me start with that. So can you see my screen which I have shared?
Yes, sir. You can see it.
Okay. So my topic is related to the soft computing technique and emerging technique in applied mathematics. Basically, mathematics, though I have written the term that applied mathematics, there is no, as such, there is no your whenever you will go in the your higher studies, you will see in after MSc that as such we cannot bifurcate like that. It's very difficult. There are many things in the pure also which is which has lot of applications. Okay, which has lot of applications in different areas of engineering and science. Like linear algebra, we think it is a pure, but linear algebra has a lot of applications in the computer science, in electrical, in electronics, in many areas. So like that. So now soft computing, when we talk about the soft computing, the term soft, it is a totally new thing came up. Just a deviation, you can say, from your deviation from your, you can say, from your or actual mathematics, or that is your the soft computing technique. That means actually when your main this classical mathematics which we are familiar with, like your probability theory or the other classical mathematics where we cannot solve. There are many your engineering side or practically the real life situations happening in the science, in management, which we cannot solve like this. Okay, there are a lot of such uncertainties came up, which is we cannot solve by those mathematics. Then this field came up. The first concept came up is your fuzzy set theory. That was given by your Jade. You are many of you may have heard the name. It's a very pioneering work he did. He's the electrical engineering fellow, but this mathematics he developed. Okay, so that is the soft computing. The start of, you can say, the soft computing, the fuzzy. Okay, fuzziness means is the vagueness. Okay, so vagueness means when there is a vague, the data, there are a lot of uncertainties and there is a vagueness is there in the data, then how can I solve? Okay, so that means suppose if I say a particular set, I have a set A and a particular variable x, whether it is a member in that set A or not, how we define in the classical mathematics, that it will be, if it is a member, obviously the your membership value is 1, or it's a non-member, membership value is 0. So these two ways we can classify the things, that one variable will be a member or not. Either a member with a value 0, 1, if it is not a member, then is a value 0. Now think about the situation that now he spread that one, that is not, say, between 0 to 1. That means it is a particular person can be a member, a particular object or a particular variable can be a member, or with a membership value is very less, not 1. That means there is a chance that it can be a member. That means, say, for example, say if I say the set of old people, now I define the set of old people as 70 and above, I can say yes, they are old. But the person with the age of 12 can come in the old, the set of old people, with your membership functions value will be very less. Maybe say 0.002 or 0.2, like that you can keep the membership value. This is the membership value with which that particular person can come in the age group of your this one, the old age group. So this is your fuzziness, the vagueness is there. There are many such things which where we use this vagueness, and based on that, main part is the decision making. When your system has to take the decision, okay. Basically, your computer, you are giving an intelligence artificially such that it can take the decision. It can do something, it can predict something, it can do the analysis like that. So when you are going to do that, so in absolute term, if you give 0 or 1, it cannot means classify in that way. Say when you are giving image and you try to classify what image it is, from there if you want to extract the things, with 0, 1, we cannot do that one, exactly. So that ranges he has made, and along with that we can make your good predictions or good analysis in this. Okay. Now, so this soft computing techniques, when we talk about, there are many things are there which comes under this soft computing techniques. One is your fuzzy logic. There is a rough set theory. After fuzzy, the development of fuzzy set theory, then the next to come up is the rough set theory came up. It was given by the Polish mathematician. And then different machine learning techniques are there. Machine learning, I have told machine learning, there are many machine learning techniques are there for different purpose we use. Like then classifications are there, clustering techniques are there, artificial intelligence, that artificial neural network is there. Your then particle swarm optimization is there, and colony optimizations are there. These are all different genetic algorithms are there. These are all comes under soft computing. There are I have given 5-6 names, but there are many more. There are many more. Okay, so if you have interest, you can go through that, and you will get many more techniques which will come under the soft computing. It's a very big umbrella under that. So soft computing techniques mainly, there are certain areas I have mentioned. It can be used for different areas. Okay. So it can be used for your speech recognition, script recognition. It can be used for image processing. It can be used for data compression in bioinformatics, health sector. A lot of applications are there. In your trading, investment, insurance sector, there are a lot of applications are there. Like that, different applications are there in your soft computing technique of these soft computing techniques. Depending on your areas of your applications, people used to choose that what type of soft computing technique they are going to use there. Okay. So somewhere you may use artificial neural network, somewhere you may use for deep learning, somewhere you can use for, if it is optimization problems are required, so you can go for those optimization techniques. Somewhere you can use for classification, somewhere you require the fuzzy logic to develop a neuro fuzzy system, we have to develop the fuzzy logic. Then so these techniques, so like that you have to take the different approaches depending on your areas of applications. Now here today, since this topic is a little bit different, I'm not going in much detail of each and everything. Just I will touch every topic with some of the soft computing techniques and some basic type of operations and their applications with some examples. Just that way we will discuss, so that you will get at least an idea what these techniques are and what are the different type of operations you can do using these techniques. That is the things I will discuss today. Okay. Now, so these are the different your applications areas of soft computing techniques. I told you. Now, so here mainly I will cover the topic, some part of the fuzzy logic. Obviously, fuzzy logic is a very vast area. Within this period, it is not possible also to finish. So some part of fuzzy logic we will discuss. Then we will discuss a little bit about the rough set, how we define the rough set, and then about the clusterings, what we mean by the clustering, which is a very important area. Lot of people are working, and different area we use these clusterings. Okay, and since we are from mathematics background, all of us from mathematics background, we have the idea of probability and other things of mathematics. So clustering is very interesting part for us, where we can work, and different works are going on. Then classifications and artificial neural networks. So these are the topics I will try to cover, and try to highlight certain things for this topics. Okay. Now let us start with this fuzzy logic. Okay, let us start with the fuzzy logic or the fuzzy set theory. Fuzzy means the main. If I use the term fuzzy, what is the meaning of that name fuzzy? Fuzzy means is a vagueness. Okay, where there is a lot of vagueness in the data. So, and where we cannot go for the probability. With the probability, I cannot solve those things. Okay, so these are there we go for the fuzzy. That means lot of vagueness is there in the data. Then we go for the fuzzy there. Now, what is that? Let me come to that part. Now, fuzzy. What is the fuzzy logic? If you see, the fuzzy logic is a superset of conventional, that is Boolean logic, that has been extended to handle the concept of partial truth and partial truth to truth values, which is the completely and completely false. That means it is in between. What I told you, that it is, yes, I am old or I am not old. We just classify in that way. Between these two, now I am spreading. So a person with the age of 1 or a person with the age of 12 or the person with the age of 30 or a person with the age of 55 or 56 or 52 or a person with the age group of 60 to 70 or like that, they all can come under that particular set, but the membership values will be very less. So this vagueness, this is a vagueness. So similarly, one example what I can give you that, say this is one example, that is your it's a rainy. Today is a rainy, might be 100% true if there is a heavy rainfall. It's 80% true if the weather is a cloudy. It's 50% true if the weather makes a cloudy and sunlight. Similarly, say for example, I want to express, say another one example, say I want to express today's weather like that. Say if the temperature, if I want to say generally means how we express. We don't say day-to-day time, if when we talk between each other, we don't say today is a 30-degree temperature, now it is a 25-degree temperature. We don't say like this. We say like this, it is your high, it's a very low temperature, high temperature, or very high temperature, it's very cold. Okay, so it's a moderate temperature. So like that, linguistically we express this. So this is a vagueness, this is a fuzziness is there. Okay. Okay, so this way we these are the places where when these vaguenesses are coming, how to deal with that. So there we with this fuzzy mathematics plays a very important role there. Then there is another one thing is there. So probability, we are all familiar with the probability, that is your either it will occur or it will not occur. Then if it occurs, with what probability will occur. So similar same thing, say here you see that there are two things. Similarly, in the fuzzy there is another one concept, there is a possibility. Possibility is based on the similarity. Okay, it is not the probability. Probability is a chance. Okay, probability is a chance, but possibility is that it is a similarity. That means it is possible that this may come into that particular group. Okay, so this is possibility. So I'll give you one example here. You can see that you have, say now suppose I am thirsty, I have a 2 bottles of water, then the rating is like this: probability of good water and possibility of good water. Probability of good water 0.9 and it is 0.5, and in other case it is another one bottle, probability is of 0.5 and your possibility is of 0.9. Now which one will I pick up for the drink? I want to have the water, which one I will pick up? So this is the uncertainty. From here the fuzzy things came up, the fuzzy logic developed, okay, the fuzzy mathematics came up to solve these uncertainties. Okay, say either you can go for the 1 or you can go for the 2. With the possibility, if you see that the 0.9 is the possibility, so I can go for the 2, and the probability is a 0.9, I can go for the 1. Now which one I will go? How we will do that? How we will deal that? Okay. So one more example let me give you, that is which day-to-day life which we take see in our life we use this one. Now this is that washing machine. Okay, that it takes the decision. How it takes the decision is the fuzzy logic is there, and based on that sensors are working. In many cases, many sensors are calibrated like that in different ranges. If it falls in that particular range, then it will take a particular state. If it falls in another range, then it will do some other activity. So like that, this fuzzy logic works. Okay. So these are the places where this is what we mean by the fuzziness, by the vagueness in the data. Specifically in the management science, in the different areas of engineering, in computer science, it's a lot of applications are there. In behavioral science, in the socio-economic problem, there are a lot of applications are there, and people are using this particular mathematics with the fuzzy logic. Okay. Now there are certain examples of different examples I have given. The names are given. That is your your k-means clusterings are there. Fuzzy decision support systems are there. Like that. Okay. So there are a lot of, the main part is the fuzzy logic, which gives it the artificial intelligence. People are using much more when you are giving an intelligence artificially to a system, the robotics or your computer. Artificially, you are giving that you are giving artificially it should work like a human brain. How our brain works, how we take the decision. There we can use this. The applications of fuzzy is that the fuzzy logic has been developed based on the fuzzy mathematics. Okay, so how is we define the fuzzy set? The definition of fuzzy set is a fuzzy set is a set with a smooth boundary. A fuzzy set is defined by a function that maps objects in a domain of concern into their membership value in a set. Such a function is called the membership function, or mathematically the fuzzy set. Each element is mapped to 0, 1. Basically, say what I told you, the membership is between 0 to 1. So it can take any value between 0 to 1. Okay, it can take any value. Now there are infinitely many values are there. So you see, you have so much flexibility in your hand to deal with the situation. It's not like that either it will be this or it will be this, not like this one. So it gives you the decision maker gets a lot of your flexibility, freedom from this type of using this mathematics. So there the membership function belongs to 0, 1. That membership can take the value from 0 to 1, any value from the 0 to that membership function is denoted by mu. Okay, so mu A is the set. Okay, A is the set and X is the element. So X will belongs to that set A with a membership function mu, which lies between this 0 to 1. Okay, it can take any value between your 0 to 1. Okay, so that gives you a lot of flexibility. You can work with the decision making becomes very easy, more flexibility. Okay, because different situations can arise. So with just only that either yes or no, we cannot handle with all these things. Okay, so this is the membership. How we define, and generally the fuzzy set is denoted by this. If the Cripps set, Cripps means the deterministic part. If the Cripps set is your A, so that A, that means suppose if I say the old people, so 70 and above anybody, 78, 71, 72, 73, 80, 81, 91, 92, 92.5, everybody comes under this set. That is the Cripps set, that is the set A. Now the fuzzy set from A, if I construct, that is denoted by A tilde, that particular notations are used in case of your the fuzzy set theory. Is a standardized your notations we use there, that is called the A tilde. And that A tilde is a fuzzy set is defined on the set A. So how it is defined, that it will take the value y with the membership of y belongs to you, the universe of this course. That is the entire set. Okay. So that is the fuzzy set we define, and that is the way how we define the fuzzy set. And this is your mu A tilde y that belongs to your 0 to 1. Okay, that belongs to your 0 to 1. Now, representation of the fuzzy set, you can see that if it is in the discrete part, the fuzzy set is defined like this: say mu A tilde y1 by y1 plus mu A tilde y2 by y2 plus like this. Now, here you please remember one thing: this plus is for notational purpose. It's not a summation. It is basically a fuzzy set where the value y1 comes with the pure membership mu A tilde y1. Value y2 comes with the your mu A tilde y2, like that. The plus is just for it set for a notation. In the notational purpose, they use that one. It is not a union. It is not the addition also. It is not the addition. Just it say basically x when a y1 belongs to that set with the membership mu of A tilde y1. Similarly, y2 belongs to that set A tilde with a membership A tilde mu of A tilde y2, like that. If it is a discrete, that the values are discrete. If the values are continuous, then we denote the continuous fuzzy set A tilde by this notation. These are all notations to represent. Okay, there is no such mathematical operations like this. Okay, that is the thing what I want to tell you. So these are the two cases: a discrete case how we denote the fuzzy set, and the continuous case how we denote the fuzzy set. Next is the features of membership function, because that is the most important part in fuzzy set. Okay, that plays a very important role. So that your membership functions can be of a different type. Now, initially when it started with the 3-4 membership, now there are a lot of membership functions are there. People are constructing different membership between 0 and 1 with different functional form. Okay. So first feature is the core. Core means it is for any fuzzy set A tilde, the core of a is characterized by full membership in the set. Hence, core consists of all elements Y of the universe of information. Okay, so that is exactly that matches. That is this one. Support is that for any fuzzy set A tilde, the support of a membership function is a region of universe that is characterized by the non-zero membership in the set. Hence, the core consists of all those elements of Y of the universe of the information such that mu of A tilde, that is the core, greater than. And between 0 to 1 is the boundary. Okay, so one is that which are within that, one is outside, and one is within that, your exactly within that particular one, that is a core, that is equal to 1, exact membership is your 1. One is the outside of these two boundaries. When I will draw, I will show you the next slide. Two boundary values, okay, 0 and 1, all other values. So like that, there are three parts we can say. For example, this. If this is your the boundary, this is the support, and this one is that. This is the core, and the support is in this entire thing. So this is that here the value is your 1. Between these two, this the value of your Y. What lies between these two, this all of them has the value membership value 1. Now here it is increasing. So this is the boundary part, and this is also this part from here to here is a boundary. From here to here, this is a boundary, and this entire part is called your the support of this. Okay, this is the way how the membership function is your denoted. Okay, it is in fuzzy set. Next is your definition of fuzzy set. Membership function. Very many membership functions are there. I'm just giving 2-3 membership functions. One which is very popular, basically, which is very popular. Many people use in engineering and decision-making problems. They use this one. One is called the triangular membership function. Triangular membership function, if you see this, it looks like this one. Your triangular membership function is this one. Okay, and if I now see this is the mathematics and mathematical form, and you see the triangular membership function how it looks like. So it is the values of your x is here, and this is the membership function value from 0 to 1. Anyone. Here the scaling 0.2, 0.4, 0.6, 0.8 like this. Now here you see it attains at a particular value that is your maximum, and beyond this is the boundary, and this is the upper another one side of boundary, the lower side and the upper side. It is increasing, then it attains a maximum and it decreases. So for one example I am giving you, all of you are generally use this. This is not reliable. The product is not reliable, or the product is reliable. Okay. The reliability, what is the maximum value of the reliability? That is your 1. So if I want to represent, apply this, your membership fuzzy logic in case of reliability, I want to represent the reliability in the fuzziness I want to introduce there. So the reliability maximum value is 1, and the other part will be between 0 to 1 anything. So this function will be very much useful for representing the reliability that way. Okay. So here it attains the maximum at a particular point, and in other two sides it is between that 0 to 1 value, that is the boundary part. Okay. Similarly, this is called a triangular. Okay. Next one is your trapezoidal function. Okay. The trapezoidal function, the mathematics is like this. That is a mathematical form is membership function is this 0 when it is less than a or greater than d, between your a to b, this is your x minus a by, like your just uniform distribution sort of x minus a by b minus a. Between b to c it is always 1, and between c to d it is your again this one. That means this. We can construct our set like this. Okay. So between B and C, this is the code, this is the maximum. It will see your sort, it will enter there. And this also can come to that particular set between A to B with the membership between that value this one. As x increases, the membership values changes. Similarly, between C to D, they can also come to that particular set. Now here it is almost 0. The membership is almost 0. This will not enter there. So this particular element here, it can say, suppose if I say this is the element here, say this is the element here. Now if you see this one, this is the element can come into this, but its membership function is very low. That means it is this one, like that it increases. It comes that means belonging to that particular set is increasing, and here it is maximum. That means sure shot it is there. Then it is again decreasing. They can also come there, but here now it is 0. That means almost going out from that particular set. Okay. So like this, we can interpret the membership function, the fuzzy set in terms of the membership function. So this is called the trapezoidal membership function because of this set. This also has applications in many areas. They use in decision making, management science. They use this type of trapezoidal membership function. Another one is also very known and useful case, you can say. This is called the base set, that is called Gaussian membership function. Other than this, there are many more. There's 5 type of things you can create. People are using many types of creating many types of membership function within that 0 to 1. So here it is a Gaussian, means that exponential 2k square. So this is your m, where it attains the maximum. So the spreads are your, sometimes it is decreasing, is a variation is very high, then obviously spread are very more, and if the variation is very less, so the spread will be less, so it is very peak like that. Okay. So this is a Gaussian part. This signal processing system, there they use it. Here also interpretation is like this. So here you see this is the membership is 0. That means belonging to that particular set becomes 0, and slowly it increases. So if you see the membership of something follows this pattern, then you can go for this Gaussian function. Depending on your, you have to choose, see the data, how it the nature of the data. Then from there, processing is very useful. This one. Okay. So now this is all about what we just a brief I have discussed about this membership function and how we interpret the belongingness of a particular your membership function. Next is your operation on fuzzy sets. There are many operations we can do. There are some basic operations now we will show. I will show here. One is your fuzzy set. There are 2 sets. So suppose A tilde and B tilde are the 2 fuzzy sets. So there is an operation called your OR. There's a union. Okay, union and OR. Union is this one. So union in the fuzzy set is denoted. It is based on, see, not by the values. In case of the classical, if you say union or addition, the values you generally deal with, but here everything in terms of the membership function. X1 is a value in the set of X and A, and Y1 is a value in the member of your, or say suppose Y1 is a value in the B, then if I do the union of these 2 sets, so member of A and the membership of B will be dealt with. With these 2, I create the membership of the new union element. Okay. Not with the addition of those 2 elements. It is basically related with the membership function. The fuzzy, most of the operations are with the membership functions. Okay. So that how we do the denote this union, this is by this notation. Similar, say for example, one example I have given is a max. This represents what? There is a max operation. Suppose A is a set like this. Say X1 belongs to this A with a membership value 0.5. X2 also a member of this fuzzy set with a 0.7. X3 is a member with a 0. This can happen that today that person who has taken part, there may be 1 day age or a 2 day age. Would be his membership function to enter in that age group of your old, that is 0. Okay, so membership with a 0. X3 with a membership 0. And B is another one, that fuzzy set, where X belongs in the set of B, that fuzzy set B, with a 0.8. X2 belongs in the fuzzy set B with a 0.2, and X3 belongs in the fuzzy set B with a 1. So here you say X3 will not belong in that particular fuzzy set, but X3 can belong here. Similarly, X2, X3, X1, they are also belongingness to that those 2 different fuzzy sets changes with the membership function. Now, if I apply this union operation on these 2 sets A and B, these 2 fuzzy sets, how? That A fuzzy set A and fuzzy set B union with a max operation. So X1 maximum of these 2 memberships at a 0.7, X3 maximum, so 0.1. So now the union is another one set. So there, these belongingness, their membership function is like this. Okay. So the operations will be like this. Similarly, the OR is the mean operator. That is this. This is the mean operator. So same thing here, membership, everything in the membership, that example is there. So when I do the OR, that means the intersection part, then it is the minimum of these 2, that 0.5, minimum of these 2, 0.2, and the minimum 0. That means that is almost like your any explicit OR sort of things which should come there. Okay, now you see complete NOT. This is another one example. Okay. So not a function. That is your 1 minus the, if I say A is Y is in the A fuzzy set A tilde, then what is the probability that Y is not there in the fuzzy set? That means A tilde complement if I want to find out. So A tilde is the fuzzy set with this membership function, then complement of A tilde, like complement set in case of set theory. When you talk about a set theory, A is a set. When I talk about that, is a complement of that means the U, if I say the universe of discourse, the U minus A, that means that entire part is your that A complement. Same thing here. How we denote that one? With the membership function. So minus, so 0.1 minus 0.5, so 0.5, 1 minus 0.7, 0.3, then like that. This is your one. So this is now A complement is the set, the complement of that particular fuzzy set A tilde. Okay. Similarly, the another one operation is different property. Like there are many now. Since I have to cover many topics, so 3-4 topics, so I'm just giving a brief idea about that. Cumulative cumulative property, it holds the cumulative property, it holds the associative property. All of you know now, we have already studied during the graduation. It holds the distributive property, it holds the idempotent property, it holds the identity property, and like that. But all these properties, if you are going to prove De Morgan's law, it holds, you have to do by the membership function, not by the values of the set, as you do in the classical set. Here, in terms of the membership functions. Okay. Now that is one thing, fuzzy relation. As you define the relations in case of your set theory, the function and then the relation. The graph theory, when you are, if you have studied the relation, you can. There's one beautiful example of the application of relation is the graph theory. Okay, if A is a node, B is a node, then there exists an edge. That means if A and B are related, then we put there is an edge. Okay, so that is the relation. So that relation we can. Just picking up this one, after explaining this, I will just explain why I have picked up that one. This fuzzy relation is your A cross B. Obviously, there is a Cartesian product between 0 to 1. How we do that one? So this this is the relation how we define in case of fuzzy. You know, this fuzzy relation, it has got an application. If you go for your in business analytics or in mathematics also, there is a thing in statistics. There is a thing called the time series analysis. Okay, that means the situations which are varying with the time the realizations you have. So suppose the rainfall data, each and every 1 hour interval if you take, so that forms a time series. Agricultural production data, that can form a time series. Every year if I take the rice production of India, so that forms a time series, okay, for 10 years, 15 years data. With that, I can do the future prediction analysis. This different organization, market research organizations, and suppose the different they take decision based on this, like that. So, for example, if you see your rice productions of last 10 years, then you can make a decision that what will be the next year, what will be on maybe the next to next year, what will be the production, how much production. If your other inputs, if you keep that the soil condition, your fertilizer, rainfall, everything like that, and then those inputs if you give, then you can find that what will be the value of the next year production. Similarly, one example is your load forecasting problem. That is electrical. That is the power generation companies. They can use this. Now, it is a classical time series I'm talking about. And it is basically deals with, it comes under the area of probability. Okay, probability is stochastic processes. So that if I now want to create a fuzzy time series, so fuzzy time series I'm going to do. There are a lot of fuzzy time series applications are there in load forecasting problems, in decision making problems, in management size, in your your trading, that your business analytics part, and any other engineering problem where there are forecasting things are there. Now, since physical situations, the data, there are a lot of vagueness that they, instead of time series, they try to do that by the fuzzy time series. So there, these relations are very much what I told you, that say I can make the linguistic variables, that is very high temperature, low temperature, very low temperature, okay, medium temperature variables. Then I have the value, the temperature where it lies. If I want to do, I have to do that. I can frame a time series using these relations, the fuzzy relations. Now see that matrix operations also we can do. How we do that one? The two fuzzy set, that matrix, suppose this one, this is one. How can I make it? Maximum of these two. Okay. Similarly, the matrix product, when you do that one, so there is the max. There is a sum is that then the max product is like this. Okay. So minimum After that, all minimum you get, and then from there take the maximum. Okay, similarly the scalar product, that is the lambda. If I do lambda, belongs to 0 to 1. So the everything comes of the this one, your membership function. Now let me come to this this one. Say example. Suppose this is one set and this is one set. Okay. Say now the addition of these two. So this is your A and B. How can you do that one? So what is that here? It says that maximum of A and B. They are membership basically. So 0.2, 0.1 maximum is your 0.1, 0.1 comes here. So 0.5, 0.1 maximum, so your like that 0.2, 0.1 comes here, then your this one, like that one by one you can create. This which one is the maximum, 0.5, 0.1, 0.15 comes here. So like that the plus operation. Now when you talk about the dot means with all minimum out of that who is the maximum. Okay, with all minimum out of that who is the maximum, 0.2, 0.1, so minimum is which one is the minimum, then 0.5, 0.1, then 0, 0, which one is the minimum. From there you can find out this one. Okay, which one is the maximum of all these minimum. Okay, similarly we create this one. So first you find out all the minimum, so minimum values are there, then from there which one is the maximum. That is that what it says that. Okay, this first is the minimum of the these memberships, and out of that which one is the maximum membership among them, that will come as your the dot here itself. Okay, so you can see these two matrices I have given. So from there you can see how it has been constructed. Like this, the different minimums are there, and then from there which one is the maximum among all these minimums, that value has been taken. Okay, so the 0.2 or the 0.1, so minimum is your 0.2. Then 0.5, 0.1 minimum is your 0.1. Then 0, 0, that is 0. So out of this 0.2, 0.1 and 0, what was the maximum? 0.2. So 0.2 comes here. So like that the others. Okay. So this is your multiplication operations you can do. Next is this is your relations. What we told you, fuzzy relations. How we have done it? Same thing, max min operation. Inside is the minimum, outside is the maximum. Okay. So this and this one, if I use these two, this row and this column, this row, using that max min operation, so this will come as your 0.4 here. Okay, so fuzzy relation you can create, and that in the linguistic variable, and you can create your fuzzy time series using this one. This is that's why I have taken this example. That is one practical example application of fuzzy relations, fuzzy time series creations. Okay. And we can do that with the fuzzy time series. In that case, the input variable will be your linguistic. That we cannot give your exact value. The linguistic variables are the input variable. And then, if a temperature is this, then in which category it will follow? It will be your high, it will be very high, it will be low, it will be very low, like or moderate, like that. So with that fuzzy relations, you can combine that one and take a decision where it will come. Okay, so you have a lot of flexibility in that way. So similarly, there are many defuzzification. So you have done the fuzzification first. You have got the values in terms of fuzzy. That means the value and the membership function. Now you need a defuzzification, the Cripps value. Then the final result will be in terms of the Cripps. So you understand the Cripps one. Okay. So Cripps value when you are going to do, then we do the defuzzification. So defuzzification is related to, there are many methods. The lambda cut method, weighted average is there, maximum, centroid. These are all simple mathematics which we understand. Centroid methods to find out the centroid. Okay. Weighted average means multiplied by the weighted divided by the sum of the weight. That gives you that Cripps value. Okay. With the membership, everything with the membership. Okay. So one just I will show you the lambda cut. It's a very simple one. Lambda cut means it defines like this. It defines like this. Your lambda is a predefined value. Okay. So if it is greater than this, then it will come there. So here you see these are the values. Here the lambda cut is your alpha cut. Sometimes they can say in some books they say the alpha cut also. Here is your x1 with this membership, x2, x3. This is after your fuzzy operations. I got this value, the set this. From here I want to construct this one, your Cripps value. So that is, if I take the lambda is your 0.6, then how can I do that? So 0.6 if I want lambda value, then which one is greater than that? So your 0.9. So that way x1 will be 1, x2 is your 0.5, and this is your 0.6. So it cannot come there. So this is your 0, x2 0.3 is 0, then x4 is your 0.3, again 0. So now among these, which one is the greater? It comes out that the value will be the Phipps value is your x1. Okay. Similarly for this one, another one example. It's a 0.1, 0.5, 0.8, 0.7, and the lambda cut is your, or alpha cut, whatever, is a 0.2. So greater than this is 0. No, this is not greater than, so this is 0. 0.5 is greater than 0.2, so this becomes your 1. Say that means it will come in the set. Now 0.8 obvious also, this also comes in the set with the possibility of 1 and then with the membership actually. And 0.7 also 0.2 greater so. Now there are 3 values which will be the 3 Phipps values. So like that you can. Similarly, the other methods are there. We can do those things because you have to make the defuzzification part after making the fuzzification part. Okay. Then there are fuzzy rule-based inference system we can create. Now I am not going to this. If you're interested, I am just share this video once more. Let me come to, because the time is short, let me come to your, there are different fuzzy inference system. There are two. One is your Mamdani fuzzy inference system. One is Sugano fuzzy inference system. The steps are there how to make this. This is the artificial intelligence part. This is artificial intelligence. First is the rule-based. You have to generate the rule-based. The rule-based one, that is the Higdonians they take, and with this fuzzification, based on that, that system will take the decision. It will go into which set, and then when you get the fuzzy set from there, you make the Phipps set and make your decision. Okay. So there are two rule-based generation. One is the Mamdani method, another is Sugano method. Okay. So these are all a little bit higher side. So those who are very much interested, after this with the fuzzy application, this is basically the fuzzy application part. Okay. How can we do that? Let me go back, come to the one more interesting theory, that is the rough set theory. Okay, the rough set, there is a difference between the fuzzy set and the rough set. Okay, what is the difference between the fuzzy set and rough set? And there is a difference between the fuzzy set, rough set, and your probability also. The probability and fuzzy, they have some restrictions about the data. Certain informations are required. So suppose in the probability, when you talk about the probability, I need the distribution. Whether the variable is a discrete or continuous. Based on that, the distribution has to be chosen. It is a discrete distribution or a continuous distribution. Now, suppose a discrete distribution. Now, discrete distribution, now which distribution you are going to do? Binomial, Poisson, hypergeometric, which distribution? Continuous, normal, gamma. So, you have to see the nature of that. So, then you can fit the distribution. Similarly, fuzzy possibilities are required. Membership functions are required. But the rough is free of all this. We don't need, just to see the data, nature of the data, vagueness of the data, then you make the classification and take the decision. That is the rough set beauty. Okay. So this was developed by the Polish mathematician, okay, very famous Paula. Paula has developed this rough set. How he has defined? He has defined the set. He has developed into 3 categories. Okay. One is the lower bound, one is the upper bound, one is the he has classified the rough set. And based on that, you can take the decision. You don't need any such membership function, possibility functions, probability distributions, nothing is there. You just see the values, the vagueness in the data, you have to make the set rough. Okay, the rough becomes, that means if the set is not the Phipps one, then it is a rough. And how the rough becomes, so you have to divide into 3 parts. That is your one is your less than the lower bound, one is the upper bound, one is the boundary part. Okay. So that, let me just come to this one. So this is the definition of rough set. Rough set theory is start feeding the data blindly from which the membership function values are computed. Here you don't need the membership, like the fuzzy set. You don't need the information of the data, like the probability. You just see that the values of the data and take the decision based on that. Okay, and make it a set the rough, and then you can take the decision. A lot of applications are there again. Mainly the artificial intelligence, image processing, signal processing. These rough set people are using. Combination of rough, fuzzy, rough, neural, everything is there. Okay, so this is the comparative study you can say about the rough set and fuzzy set. Okay, fuzzy set we need this membership function and other things. In the rough, this is not required. We can directly just go for, on the other hand, rough set is a certain mathematical tool for solving the uncertain mathematics. In the fuzzy set, we need the membership function and then we can solve the uncertainties. Here we don't need that and we can solve the uncertainties. Okay, so how we define let me just quickly come to that particular thing in the rough set definition. Basically, information system. Okay, information system and a decision system. Together, there are object, there is an attribute. Okay, the object X. So suppose in an age group, age is an object. Okay, 50 years, 60 years. Say suppose different age group I can make. And so suppose my muscle strength. One example, just I'm coming to that. Whether with that muscle strength in that age group can walk or not. That is a decision. Walk is a decision. Muscle strength is an attribute, and I am a person X. Age is an attribute. X is an object. X belongs to this particular age group. With this your muscle strength, can he or she walk or not? That decision has to be taken. So this is the information system, decision system. Okay, this is denoted by DS, and IS is the information system. So this is U is the entire set, A is the attribute, U is the object set, A is the attribute set. So there is a relation. Okay, here we take here how he has defined. He has defined by and transitive. Okay, reflexive, symmetric, and transitive, and that there he has defined a term that is called indiscernibility. Indiscernible means the object cannot be represented very well. Discernible means I can represent, I can recognize the things, but I cannot recognize in very well. That is indiscernibility. When it is indiscernibility is there, then it becomes a rough. It becomes a rough one. That is the definition of your. Then some attributes become overflows. Okay, you cannot. Sometimes you get the same attribute you yes. Sometimes you say with the same attribute you no in some age group. So this indiscernibility is there. So that is the roughness created. Okay. So there indiscernibility, how we define? We define with this mathematically, we define with this one. That means it belongs to this where X, R, Y. R is the relation. Relation that follows 3. That same what we know, reflexive, symmetric, transitive. And then it is a indiscernible means whether it comes into that particular core group, that means the lower part, lower bound, that is that one. Another upper, that means outside, that means yes, no. May come, may not come. Another one will not come. Okay, so that particular part is the indiscernibility. With that particular information, with respect to B, B is your attribute. B is the attribute. Okay. Now you see here one. So this is the rough set definition. How? R upper, R lower. Upper is this, which will directly that will belong to that particular set. That is upper. Lower, sorry, that is lower. Upper is may belong, may not belong. Combination of those two, that is there. And now minus, if I say minus of this, that gives you the boundary. Okay, that's original set X minus this, your lower, that gives you the boundary. So boundary and is for the boundary, which will not come that side. Okay, that is the way the rough set is defined here. Now see, this is a one example. This is your. This is not attribute. This is basically the objects. These are the two attributes, the age and length. Length is the muscle strength. Okay, and this is the decision. Okay, here you see in the age group 60 to 30, that 50 limbs are there. They can walk. 60 to 30 with the 0 limbs. Limbs is a muscle strength. Is a muscle property. 0, then they will not walk. That X3, that object within that age group with this muscle strength, they know they cannot walk. Now here you see X4 with this same. They may walk. So there is a superfluous part. This is roughness comes here. Okay. Same thing here also. Here the roughness comes here. Now how you do that one? So now with this attributes, what are the different attributes? Age and limbs are the attributes, and these are the different your values. And with that, if I do, then you see the say indiscernibility with respect to age. If I create. What is the indiscernibility? That is X1, X2, X6, one group. That means equivalence class. Basically, it is a creation of the equivalence class with this relations. Okay, the relation, if it follows all these three, then that is the one equivalence class. That is the granular computation. Now people are talking about granular computation. This is rough shape. So this is one granule. So X1, X2, and then X6. So these three, age-wise attribute is your age. They follows one your equivalence class. Okay, that is one indiscernibility. Similarly, X3, X4, they create one. Okay, X3 is what? 30 to 40, 31 to 45, same age group. Okay, and this. So they form one granule, one your equivalence class. Similarly, this one. Okay. Now, similarly, your another one is your X5, X7. If you see that example, X7 with respect to age, X5 is 40, 46, this 46. So with respect to, then again, they want equivalence class. Similarly, with respect to lengths, that is a muscle property. Now, muscle property, if you see that this is exclusively 1. They cannot group with any other. Equivalence class will be only 1. Here also only 1. Now, these two, with the limbs, these two form 1. With the limbs, these two also form 1. Okay, these three also. So here you see, so limbs are 1. X1 is 1, X2 is 1, X3, X4 1, and these three are 1. So this way, it comes under your, it creates one business underrated. That means one different groups of your equivalent classes. Now with age and lengths, if I do, with age and length, it is your this and this together. Together, if I do, then it becomes your x1, x2, x3, x4, x5, x7, and x6, 1. So x1 is x group and this length together, there is no other which can come here. So this is 1. This is also 1. Now these two, they can come together, same age group, same lengths. Now here the roughness. The same age group says some data says no, some data says yes. Some can also work, some cannot say they are not working. So this is a roughness comes here. Okay. Similarly, like that, this is your indiscernibility. Now here, what are those your lower bound? That is your R dash. One is your x1, x6. Based on that one, you can find out here which will sure shot goes there. Okay, x1, yes, sure shot goes there. x6, yes, 16, 30 with this length, sure shot it goes there. So this is your this one. Similarly, R double dash, yes, no, they can come, they may not come in that cases. Okay, so that is your x1, x3, x4. x1, x6 will be there because when you are considering lower is included other than this who are there. Okay, so that means which can come, which may not come. So that is your, here it is given your x3, x4. So x3, x4 is, let us see what is your x3, x4. x3 is this one. It is this one and x4. So in this case, it may come, it may not come. So that means this, and these two. So this is the upper construction. Okay. So this way, now the entire set, if I subtract this one, this value, then whatever the remaining, that creates the boundary. Okay, that creates the boundary of that particular rough set. So rough. So this is your inner part, which is your shot. One is your this part is your this one, and another part is your boundary part. Okay. So this is where you create the rough set. Do we have time? There are different examples for this. There are many other things that there. Should I proceed? Yes, I think it is up to 12. It is 1 o'clock.
Yes. Yes, sir. You can take a maximum 5 minutes.
Maximum 1 o'clock. Okay. Then let me come to this, instead of this slide, let me come to another one very interesting part. That is another one part of your. This is your Bayesian. Now I have talked about the fuzzy set and this one. Let me do this Bayesian. Bayesian belief network. This is also one soft computing technique. So this network is your acyclic directed graph. Okay. So it is something that the dependency relations. This is probabilistic, totally probabilistic part. Okay, this is also very much used in information system processing. The Bayesian belief network is a lot of use are there in computer science. Image processing, specifically with your neural network, they use it. Suppose the season is your rainy season is there, then this can rain, can cause an allergy. If the rain is there, the grass will grow. If the rain is there, umbrella is required. The season is rainy season, then also umbrella is required. If it is a summer season, then also umbrella is required. So umbrella required for many things, for seasonal. That means for rainy, for summer. If the rain is there, umbrella is required. The season wise also umbrella required. Rain is there, umbrella is required. If rain is there, grass will required. So if the dog barks, then the cat will hide. Like that, you can say if your rain is there, season, say in the winter, we have allergy. In the summer also, due to heat, we can have allergy. In the rainy season, we can have allergy. So due to season, we can have allergy. So this is the dependency relations in your probabilistic we can do. Okay, that you can make a network sort of things because this structure, because of this structure, network structure is a network. There is a Bayesian belief network. So here you have an example of this. Suppose you get late, or say you wake up late, so you can reach to the school your late in a delayed time. So there will be a scolding from your teachers, or there is a traffic jam. For that also you can be delayed. And for your father, say there is another 1-2 events are there. That is there is a traffic jam. You denotes that your father boards the public bus in the morning. Okay, he is an event that, and if that denotes the event your father goes to the office. Okay, now if I want to make a Bayesian belief network, so what is A? A is you are waking up late. And what is D? D is that the event independent. So here you see A, B, C, and the event D is independent of E and F. So here you see E and F is for your father. So that is no way related to you. Okay, so you can find the dependency relation like this. And D, if there is a traffic jam. So school late because of delayed this one or because of the traffic jam. Any one way you can this and happen. And because of this delay, you will get the scolding. But this will not take place, this scolding and going to school late, not for this part. So they are independent. So there are two different networks you see. And how we compute the probability? First you have to do this probability. This probability table we create using this network. Okay. Then probability we can find out. Now from here I can find out this conditional probability. What is the probability that you will get a scolding? So probability of getting scolding is like this. Not depending on E and F. It is this conditional probability we can calculate. So with this BBN network we can use for finding out the probability. So we can make this your dependency relation. Using that you can make the graph and the probabilities we calculate. So this is another soft computing technique. And that was the thing what I was talking about, the clustering, which is also a very important one. That means classification of the objects. Okay, similar type objects in one group, that is for the cluster. Okay, similar features, similar type objects. Suppose all red star are with this one cluster, these all group green balls are in one cluster, then these are also in one cluster. So I have this, I want to classify these into different clusters like this. Okay. So there are different techniques. These classification techniques are the clustering techniques are making the book. Clustering is a unsupervised learning technique. This is unsupervised and supervised means your what? So I am teaching in the class, my students are learning. So this is a supervised learning. Okay, you are working in the class, your teachers are teaching. So that is a supervised learning. But so suppose you are giving a food to a dog. So suppose you are giving a food to a dog in a certain place. Today you take that food, just sow the food, and the dog will come with you and say place is fixed where you have to feed that dog. You keep that food there. So next day the dog will know that it has to go that particular place. Then it will get that particular. So automatically the dog will learn itself. There is no supervision. No teacher is there. Dog will learn it itself. Is unsupervised learning. So the dog knows that it can go to that spot to get the award. Okay, that is the food. So automatically it will learn. That is your unsupervised learning. The clustering is that. It's the unsupervised learning. Okay, we are not training that one, the data. Automatically it will cluster. It will form the group between them, and you will get the different. It has got a lot of application in cancer diagnostics, healthcare, lot of in psychiatric problems. We can make use of these clusterings. In your mobile network, you see there are mobile towers are there too. Wireless networking. There are a lot of applications are there. Okay, so like that, these are hard clustering, C-means clustering, there are hard clustering. Now fuzzy is also there. Fuzzy people are using to make the clusters. Okay, cluster algorithms people are developing. That is for the fuzzy cluster. The clustering is a one which is very important. So that K has to be identified. Suppose 2 clusters, 3 clusters, okay. Then those many, you have to see now, there are 3 clusters now. First you initially partition. Now first partition, now you have to say here you see that data. Now I want to find out the centroid value of this. I want to find out the centroid value of this. I want to find out the centroid value. Here K is 3. The 3 centroid. Now suppose this centroid here it lies here. Now who are close to this and who are close to from here this, who are close from here this. So I'll from this they will come there and the others will be discarded. Similarly, this centroid who are close, so that will form one cluster. So the cluster will what happens? It will iteratively change, modifying that a reallocated part goes, which is choose the nearest center. One example like this. So suppose this is the data points. I have made this. This is one data point for these. This is one centroid. This is one centroid. So two clusters I am making. So one centroid. Now who are close? These are close to this. So this is one cluster. These are close to this. This is one. That means Euclidean distance. Distance is the clustering. There are Euclidean distance or distance. You are all familiar. You are not know that. Okay. So that distance. So this is the cluster. This is the cluster. So we are doing the classification. Now again, now this cluster again one centroid I calculated. So updation of the computation. Now here also I have calculated. Now who are from here close to this? Who are from here close to this? So that point comes here, and now here again change. That some are already out. This point is out from this cluster. So this point is out. Those who are there, this is here. Then here also who are very near, so these and others are out. So now finally we got the base two clusters like this. There are different measures to get these clusters. Okay. So this is the way how we do this clustering. The examples are there. The Euclidean distance calculation. You take two clusters, so 2 points. Two farthest point. One is 1, 1. One is 5, 7 considered, and based on that others Euclidean distance computed. So from there you see there are two clusters. One is very close to 1, 1 point. One is very close to your 5, 7 point. So for these points, what is the centroid? You calculate using this your that means what the mean value. So mean you are calculating K means either the median or the mean you calculate there, and for this that mean of the distance you calculate. And then again reclustering you are doing. So like that you can frame different clusters. So this is clustering part. And similarly there are classifications. So you say SVM is there where we find out the planes. Okay. Then that is the support vector mechanism, which is very little bit higher side at this level for graduation. But those who are very much interested, they can carry forward. So this distance maximization. Further distance will not consider, which are very close. That hyperplane we will find out using this one. Another technique is the artificial neural network. So this I think it's time already. Let me stop here. You can see this. So if you have any queries from here.
I thank Dr. Chatterjee for giving such a...
Can you a little bit louder in front of you?
Am I audible, sir?
Yes, please tell me.
Okay. I thank Dr. Chatterjee for giving such a valuable and inspirational presentation. It enlightened our knowledge on the topic soft computing technique. Lots of knowledge we get from the sir. There are many questions from audiences. I like to ask a few, sir. So most of the questions which are asked by the audiences, they want to know what is membership function, sir.
Membership function, Faji said, that is the thing what I told you. So suppose it is the degree of belongingness. A particular value will say, suppose X to that particular set. How much degree of belongingness? Say with the age of 80, he is obviously, certainly he will belong to that age group. That is your old set, old set of people, that set. But age group of 1, that can also come to that set, but its degree of belongingness is to be almost in the side of 0, 0.00000 maybe 9, 0.0000001. That means this is the membership. That means its degree of belongingness is there, but very vague. That is very less, that part. But other cases it is this one. So that is that. The membership means it is the, whether it will be a member of that or not, that belongingness, degree of belongingness we denote by the membership function.
Okay, thank you, sir. So here we have another question from the audiences.
Right, please.
How fuzzy logic is related to the soft computing?
How fuzzy logic is?
Related to the soft computing.
Computing is this one, the fuzzy. There, when there is a vagueness is data there in the data. Okay, the data we cannot interpret that way. That is strictly it will be there or that way. Okay, so you have to take the decision. Suppose you have an image. Okay, so the image is very blur. It's a blur image is there. Suppose my face. How can you recognize it is my face? My eyelids, my nose, my teeth. So there is a fuzzy logic I can create. I can create the membership with this your that. When image basically we classify with your intensity of the light. So with that, if it can create that belongingness, so we can create the logic. So if this happens, then the system will take that decision. If it falls to some other membership, then the system will take another one decision. So like that, you can make that fuzzy logic. If then else, if this, then this.
Okay, sir. Thank you. Sir, I have another question.
Right.
This is asked, which is better, fuzzy or rough set theory?
Hello? Pardon?
The question is that, which is better, fuzzy theory or rough set theory? Which get better?
This is very difficult. Again, a fuzzy question is very difficult to answer. Both are equally good. We can go for fuzzy, we can go for rough, but rough has lot of, though rough use is very less, now people are using. Earlier it was not that popular, but rough is more flexible because if you don't need all those restrictions on the data. Directly you can just apply, see the attribute, their values and take the decision. Okay, so there. So that's why rough is, in that way, rough has the advantage over fuzzy, you can say. Okay.
Okay, sir. Thank you. Sir, once again, thank you so much for your informative session. Now, I request Prakash to continue the session.
Well, thanks, Partho. It is great pleasure for me to introduce our last speaker of today's webinar, Dr. Snehasis Kundu, Assistant Professor, Department of Mathematics, NIT Jamshedpur. He has done his BSc from Calcutta University, MSc and PhD from IIT Kharagpur. He received several awards and fellowships. He was awarded Young Scientist Award and Outstanding Scientist in Mathematics from Venus International Foundation in 2016 and 2019 respectively. Yearly Career Researcher Award from DST SAR 2017, Institute Silver Medal from IIT Kharagpur for securing first position in MSc 2010. He has published more than 25 research papers in International Journal of Report. Currently, 3 students pursuing their PhD under his guidance. So now I request Dr. Kundu to deliver his talk.
Am I audible?
Yes, sir, you are audible.
Thank you, Prakash. First of all, I would like to thank all the members of the organizing committee for inviting me for this one-day webinar on current studies on applied mathematics. Today, I'll discuss on something which is related to, because maximum audience belongs to the graduate and postgraduate students. So I choose the topic of the fractional derivatives and fractional integrals. So I'm sharing my screen. Please let me know whether it is visible or not. Is it visible?
Yes, sir, it is visible.
Okay, so the title of the, since all of us has from the mathematics background, so all of us has an idea what is the normal derivatives and integrations in the calculus. We have already studied them. Today we are going to discuss something which are, the topic is very old, but nowadays in many fields it has a great applications. Okay, so the title of presentation is the fractional derivative and its application in various fields. The outline of the presentation will be like this. First, I will discuss what is the origin of this fractional derivative and fractional integral. Then I will discuss about some special functions. Special functions plays a very important role in this fractional calculus. And then we will introduce first some different kinds of definitions of the fractional derivatives and fractional integration. And we will discuss some examples. And we will look upon some applications, how we can apply them to some fields. Okay. So the topic is actually undercovered the general topic, which is called as a fractional calculus. Fractional calculus, it does not mean the calculus of the fraction numbers. Rather, it is the theory of derivatives and integers of some arbitrary order. So it has a very old history. In 1695, when Leibniz introduced the notation of derivative in x to the power n, another derivative of a function y, then L'Hopital wrote a letter regarding asking the question that what could be the value of this derivative when we take the value n is equal to 1 by 2. So at that time the answer was not known. So therefore Leibniz wrote back to L'Hopital by saying that this is an apparent paradox, and from which one day useful consequences will be drawn. So from this, many mathematics at that time started working on this field, which is today which is generally called as a fractional calculus. More specifically, fractional derivatives and fractional integrals. So in later on in 1695, Leibniz introduced a general order definition on fractional order derivatives. And after that, Euler used the concept of the numerical interpolation technique to define the fractional order derivative. If you have a two fractional derivatives of integer 1 and integer 2, we can interpolate them to define the fractional order derivative. So that is the process that the Euler has employed at the time. And after this, in 1812, Laplace introduced the fractional derivative by the means of an integration. Okay, and after that, in 1819, it is the mathematician S.F. Lacroix who has given the answer of the question, what could be the value of this nth order derivative when n is taking the value 1 by 2, and he give the formula number this equation d half y dx to the power half will be 2 into square root of x divided by square root of pi. Okay, so he has got the result by using the concept of the nth order derivative of a function x to the power n. So if we use instead of the factorial notation, if we use the gamma function, so the nth order derivative formula can be expressed into equation number. In 1822, Fourier also gave a different kind of definition for fractional derivative. So Fourier, we all of us know what is the Fourier series. Any periodic function, or even if it is not periodic, you can also express them in terms of a Fourier series. So taking the help. Then 1823, Abel was working on the solutions of the integral equation, where he had defined what is known as the Abel integral. So he found that the Abel integral in the equation number 4, this expression can be expressed in terms of a fractional derivative into this form. And from equation number 4, he get the equation number 5, which is d to the power half k. K is a constant number over here, and ds to the power half, that the fractional derivative of a constant, it is expressed as a root 5 into fx. So this is a very interesting result, which shows that the fractional derivative of a constant is no more 0. So generally we have the idea that the derivative of a constant is always 0, but this result is not true in case of a fractional derivative. So it may not be a 0. So this will discuss later onwards in our slides in a detailed manner. So after that, the mathematician 1869 mathematician Sonin, he has introduced a different idea to define the fractional integral of a function. So he has used the Cauchy integral formula from the complex analysis, and by using the contour integral, he got the formula which is given in equation number 6. Okay. And then Liouville first introduced a different definition in 1930, different definition of the fractional derivative of a number h to the power minus a. A is a real number, it can take the value greater than 0, and he using the gamma function, he obtained that the formula can be obtained into this form. The fractional derivative, alpha third fractional derivative, is represented into this form. So if we look into the equation number 7, there is an interesting thing to look out. If we take the limit a tends to plus 0 plus, from the right hand side, if we take the limit a tends to 0, so gamma a is tending to plus infinity. So as gamma a tending to plus infinity, the value. So if you observe that the left hand side, when a taking the value 0 or it tends to 0, this is basically merely comes to a constant value. And we are seeing that right hand side, it becomes a 0 value. So equation number 7 indicates that the fractional derivative of a constant number can maybe also 0. So in this main point out too is that we have two definitions. One is given in equation number 5, another is given in equation number 7. So these two definitions shows that sometimes if you are defining a fractional derivative in a manner, but the constant of the fractional derivative may not be 0, but if we define it in an alternate manner, constant of a fractional derivative may be 0. So from now this onwards, the beginning of the study. So if we look that in this definition, some gamma function we have used. So before going to the original definition of the fractional integral or fractional derivative, we will discuss some special functions because special function plays an important role in the definitions of this fractional integration and derivatives. So the first special function, it is we are taking what it is called as a gamma function. If x is considered as a real variable which is greater than 0, then the gamma function is denoted by this symbol, and it is defined by this improper integral e to the power minus 2 to the power x minus 1 into dt. So for the positive values of the real number x, so the plot of the gamma function will be look like into this form. So as x tends to 0 plus, so the function value approaches to plus infinity, as well as x tends to plus infinity, x tends to plus infinity, the functional value also approaching to plus infinity. And at the point x equal to 1, the function value takes the 1, and at the point x equal to 2, the function value also takes the value 2. So this is the main definition of the gamma function when the x is a greater than 0 real number. So this gamma function satisfies some very interesting properties. So first of all, it is a positive number when x is greater than 0, and it is continuous and differentiable whenever x is taken as positive. Gamma 1 value is equal to 1. It can be easily obtained by the definition of an improper integral, and it is called as a recurrence formula. Gamma of x plus 1, it is any real number. If we express any real number into this form x plus 1, this is same as a gamma x into gamma x. It will hold for any real number x is greater than minus 1. So this, and in particular when x takes the value from the natural number, the gamma n plus 1, it is equivalent to the factorial n. Okay, that is the reason that the gamma function, it is called as a generalized factorial notation. So this slide gives the complete plot of the gamma function, all for positive values of it as well as the negative values of x. So if you can observe that, so this part is already we have discussed. This is the negative part of the for x is negative values for this. So and it is coming as an alternate manner. So this is known as a generalized factorial notation. So if you, for example, if you have a number in, which is in between 5 to 6, suppose you are thinking of at a number 5.5. So if you have the number, if you want to write gamma 5.5 value, if you want to calculate, so this value we can write it as a gamma of 4.5 plus 1. So using the recurrence relation, we can further write it as 4.5 times gamma of 4.5. So we can see that to calculate the value of gamma 5.5, we need to find the value of gamma 4.5. So from this point onwards, so 5.5 onward, we are basically go one step backward to the point 4.5. Similarly, we can repeat the same step once again. So if we repeat the same step from 4.5 value, we are going to 3.5, and then from 3.5 we are going to 2.5, then 2.5 we are going to 1.5, and 1.5 we are going to 0.5. So the 0 point value, gamma 0 point value is equal to half. It is square root of pi. Gamma half value is square root of pi. So from this, by using this product formula, we can calculate what is the value of gamma 5.5. So this is a picture of when gamma x is any real number. But if in particular, if you have a integer number, when you suppose you want to calculate what is the 5 factorial, so basically at this 5 point you are here. So from 5 you are going one step backward. You are going to the 4 factorial, then you are going to the 3 factorial, you are going to the 2 factorial, you are going to the 5 into 4 factorial, and etc. etc. So in case of the normal factorial notation, you are going one step backward but in an integer step. Or in case of a gamma function, you are also going one step backward, but the step is no longer integer, it can be any real number. Okay, that is the reason that the gamma function is known as a generalized factorial notation, factorial function. Next special function is called as a beta function. It is a function of two variables. So beta, it is denoted by the notation beta xy, and it is defined by this improper integral 0 to 1 t to the power x minus 1 minus 2 whole to the power y minus 1. And the integral is convergent when x greater than 0, y greater than 0. And this is since it is a function of two variables, x and y are two independent variables over here. So the plot of this will be a surface, and this is the plot of the beta. We can write it in terms of the gamma function, gamma half into gamma half divided by gamma half plus half, which is gamma 1. So basically gamma half whole square, and since gamma 0 is positive, gamma 1 is greater than 0, gamma is positive. So we are taking only the positive sign, so it is equal to square root of pi. Okay, so these are some properties of the beta function. Next, we are going to discuss the function which is called special function, which is called as a Mittag-Leibler function. This is the generalization of the exponential function, and it plays a very important role in definitions and solutions of the fractional differential equations. So all of us know what is exponential function. So and introducing the different number of parameters, exponential functions are generalized in this manner. So the Mittag-Leibler function for the 1 parameter and 2 parameter are defined by equation number 10 and equation number 11. So you can observe that E alpha z, it is z to the power k by gamma alpha k plus 1. So it is a 1 parameter Mittag-Leibler function, and it is if we replace this one by beta by introducing another parameter, extra parameter, so it is z to the power k by alpha k plus beta. So this is called as a 2 parameter Mittag-Leibler function. So these two Mittag-Leibler function covers many special functions, many other functions, exponential functions, trigonometric functions, and hyperbolic functions. Here are some few particular cases. So we can observe that when beta value is equal to 1, so if you take beta value equal to 1, this definition reverts to the previous one. So for 1 parameter, Mittag-Leibler function, and if you take alpha and beta both values are equal to 1, so then it is z to the power k by gamma k plus 1. K is an integer over here, so then gamma k plus 1 is nothing but the k factorial, and z to the power k by k factorial, this summation, it goes back to the exponential function. Similarly, if we keep on increasing the beta value, instead of 1, if we choose beta equal to 2, e1 to z, it is expressed by the function in the compact form, e power z minus 1 by z, then beta equal to 3, e power z minus 1 minus z divided by z square. So it does not only contain the exponential function, it also contains the hyperbolic functions, means sine hyperbolic and cos hyperbolic as some special cases. So if we replace z by z square and alpha is 2, beta equal to 1, so you will get the series expansion as z to the power 2k divided by 2k factorial, which is nothing but the cos hyperbolic z function. Similarly, if we replace beta, if we take beta value 2, we will have the sine hyperbolic z function. So these are the two particular cases for the hyperbolic functions, and there are the trigonometric functions. Sine function and cos function can also be represented. So if we replace z by minus z square and e to 1, alpha equal to 2, beta equal to 1, so we have the cos z function, and if we replace them, alpha is 2, beta is 2, and then we have the sine z by z function. So these are the plots of the Mittag-Leibler function of first kind and Mittag-Leibler function of 2 parameter for different values of parameter. In this case, alpha equal to 1 value, this gives the exponential function. I have only choose the range of z from 0 to 5. So if we look at the green continuous line, this is the exponential function curve, e power x. Alpha, when alpha equal to 1, it is actually same as the exponential function. So it is the exponential function graph. It takes the value 1 when z is equal to 0. So if we keep on decreasing the value of alpha 0.9, 0.8, 0.7, the curves goes more steeper. And if we increase the value of alpha from 1 onwards, 1.1, 1.2, 1.3, the curve becomes flattened. So these are the this shows the variation of the Mittag-Leibler function for the parameter alpha. So similarly, here we choose the value alpha equal to 1 as a particular case, and we have only checked the values for some beta values. So you can observe that beta equal to 1, this is the green dotted line. This line is the exponential function, and like this, the variations are occurs. So this like this, it can cover the all other functions also. Now, these are the two different definitions. So not only these are the only definitions, there are more generalizations to the Mittag-Leibler function. There are 3 parameter and n parameter definitions are also available. So only we are in our discussion we only focused on 1 and 2, and this is the definition for a 3 parameter Mittag-Leibler function. The 3 parameter alpha, beta, delta Mittag-Leibler function is defined into this form. So it is also a more generalization regarding the 2 parameter or 1 parameter, and it reverts back to the previous 2. If we choose beta and delta both are 1, it is the I alpha, and if we choose the delta value equal to 1, it reverts back to the 2 parameter function. So in this definition, this delta k is used here. This is here actually Posema's symbol. This Posema's symbol for a real number alpha of n, it is defined by this definition. When n is value is equal to 0 and alpha not equal to 0, it takes the value 1, or it takes the value of this n products, alpha, alpha plus 1, alpha plus 2, alpha plus n minus 1, when n takes the value 1, 2, 3 onwards. So this definition is used over here. So next special function is called as a right function. This is also a one kind of generalization to related to the mid-tech leveler function. So the right function of two parameter, right function of two parameter alpha beta, it is defined by this infinite series z to the power k by k factorial into gamma of alpha k plus beta. So this also covers some previous function. The exponential function can also be covered from this right function if we choose alpha equal to 0, beta equal to 1. So then it gives us the exponential function. And if we replace z by minus z, alpha, beta, both values are minus half, then we have the e to the power minus z square by 4 function. This function is a very important function because this is nothing but the Gaussian or normal distribution function in case of the probability distribution. And here also these are the some variations of the right function for the interval of z from 0 to 2. Beta alpha is 0, beta is 1 is the exponential curve. So this green line is denotes the exponential curve. As soon as you increase the value of beta, the curves lifts upward. If you decrease the value of beta, the curves go to the downward direction. So it varies into this manner. Another important special function is which is called as a hypergeometric function. So the hypergeometric function of two set of parameters. First set contains the p number of parameters alpha 1, alpha 2, alpha p, and second set contains q number of parameters rho 1, rho 2, rho q. Then the hypergeometric function for these two set of parameter and for the variable z, it is denoted by this notation, and it is defined by this infinite sum. So here in the numerator this Cauchy symbol has been used, and in the denominator also the Cauchy symbol has been used. So which we have already defined in the previous slide. So this hypergeometric functions also includes some standard functions. For example, the exponential function, the power function, binomial function 1 plus z will be the power alpha, the logarithmic function, sine function, cos function, and inverse sine function and inverse cos function. So they can be recovered from this hypergeometric function for some special values of these parameters alpha 1, alpha 2, alpha p, and rho 1, rho 2, rho q. So exponential function is obtained if you set if these two sets are null, there is nothing in this set, means the p value is 0, q value is 0, there is no element into this set. And if we set only the z variable, then in this numerator this value is not present. In this denominator, this value is also not present. So it will simply revert back to z to the power k by k factorial, so it gives the exponential function. So like this, all the functions can also be derived using the hypergeometric function. So now, so these functions we have introduced. They are used in some solutions. They are used by sometimes to defining the fractional integrals and fractional derivatives. Now we are going to first introduce what is called as a fractional integral. There are different kinds of definitions for the fractional integrals are there. Here we will discuss some few of them. One of them first is which is called as a Riemann-Liouville fractional integral. So to defining the Riemann-Liouville fractional integral, before going to the main definition, we are just using a iterated integration over here. We are considering the integration. I am denoting this integration sign by this notation d minus 1. So minus sign here, it indicates that it is an integration. So it is basically defined, it is denoted as an integration 0 to t f tau d tau. Then d to the power minus 2 means it is a integration twice, two times integration, or the double integration. So it is defined by this 0 to 2 d tau 1, and then integration from 0 to tau 1 f of tau function of the d tau. Similarly, the n-fold integration is defined as d to the power minus n. It is 0 to t d tau 1, 0 to tau 1 d tau 2, then 0 to tau 3 d tau 3, and etc. 0 to tau n minus 1 f tau d tau. So now we are first trying to understand that if this is a this is a double integral, next we will have a triple integral. So like this, gradually this is a n-fold integration. So we are saying that this n-fold integrations can be expressed in the form of a compact integration, which is expressed into this form: integration 0 to t kn t tau f tau d tau. So if we can observe that if we compare this equation with the first equation, we can see that if we set kn, the function kn theta is equal to 1, so this reverts back to the first integration. Similarly, if we set the value n equal to 2, if we set the value in n equal to 2, then we have this double integration. So after changing the order of this double integration, this integration can be represented into this form. So if we compare it with this k definition, so the k function over here, it is actually t minus tau. Similarly, if we take a threefold integration n equal to 3, so the k function takes the form t minus tau whole square divided by 2. So in general, we are if you do the induction principle, so by using the induction principle, we can write the nth term kn as t minus tau whole to the power n minus 1 divided by n minus 1 factorial. This n minus 1 factorial can be represented in terms of the gamma. It is as a gamma n. So if we substitute this into this equation, the dn n-fold integration of a function ft can be represented as 1 by gamma n integration 0 to t minus tau n minus to the power n minus 1 f tau d tau. So basically, we are saying that any n-fold integration can be put in a compact form using a single integration. This function over here, t minus tau whole to the power n minus 1, it is called as a kernel of this integration. So now we are so here in this case, if we all these things, all the derivations over here, we are considered n over here, n is as an integer. So now if we free this free this integer n to take any real number, the Riemann-Liouville fractional integral can be defined into this equation number 2.1.2. So what are the things we are assuming? We are assuming that ft is a piecewise continuous function over the interval 0 to infinity, or any sub interval 0 to infinity. Then the fractional Riemann-Liouville fractional integral can be denoted by this symbol. So here the minus sign indicates it is an integration, and nu is any real number. That the definition is given in a complex number, but you can take any real number. Nu is any positive real number. So then the integration of this is defined. Fractional integral of order nu is defined as 1 by gamma of nu integration 0 to t minus tau whole to the power nu minus 1 f tau d tau. Okay, so here this 0 and t, these are the in the notation 0 and t, they are called the terminals of the fractional integral, and they actually set as the range of the integration in the definition 0 to t. Instead of 0, if we said it is starting from a onwards, then the integration will also be from a onwards. Okay, so this is the basic definition which is known as a Riemann-Liouville fractional integral of a function ft, which is defined over the interval 0 to infinity and piecewise continuous. So let's take an example how we can calculate the Riemann-Liouville fractional integral of some function, some standard function. So here we consider a power type function t to the power mu, and mu value we are setting as greater than minus 1. This is required for convergence of this integration. So and we are assuming that this function is Riemann integrable. So then the Riemann-Liouville fractional integral of the function, it is by definition is this function. Then using a transformation, this integration can be represented as a beta function. Then further using beta and gamma relation, we can write down the fractional integral of the function t to the power mu as into this form. This is very convenient with the previous standard knowledge. For example, if we go back to the standard integer cases, if you said new value is equal to 1 and mu value is also set is equal to 1, then this left hand side, this actually defines t to the power minus 1 means it is integration of t of dt. Okay, integration of from 0 to t and of the function t dt, tau d tau. So basically, if we look into this, put the value of the mu equal to 1 or mu equal to 1, so it will have a gamma 2 and divided by it will have a gamma 3, and it is t to the power 1 plus 1, it is 2. So if we simplify it, gamma 2 value is 1 and gamma 3 value is factorial 2, which is basically 2, and it is t square. So it reverts back to the well-known formula, because you know that the integration of this basically t square by 2. So which is we are getting the same result as a particular case when we set them as a integers. Okay. So this Riemann-Leibniz fractional integral is a generalization to the standard integration techniques for the integer orders. So here, one interesting property of the fractional integral is that we know the standard property that if you have an integration of an integer order, if you have a function ft, if you integrate it twice times and then if you integrate it 3 times, so basically the result will be same if you integrate it thrice first and then integrate it twice again. So in case of the fractional integrals also, the result also holds. So it means that if you have a function ft, if we integrate, if we do the fractional integration of order mu, and then if we do a fractional integration of order nu, then the result can be commuted. So you can the result is same as if you do the integration of a fractional order of order nu first, and then if you have do the fractional integration of order mu. So it can in algebra this property is known as a commutative property. So the Riemann-Leibniz fractional integral satisfies this property. So you can commute between the order of the fractional integrals. The proof is very simple. So starting from the left hand side, if you write down the definitions one by one, so this definition can be represented in terms of a double integral, and using a simple technique of a substitution, you can change the integral, and using the beta function we can get back to this result, which is same as if you do the, it is also says that if you have a 2 times repetition fractional integral, so the result will be same if you perform a single fractional integral of the order mu plus nu times. Okay. So next result is regarding the fractional integral of a derivative of a function. If you have a fractional integral of order minus nu minus n, and if you are doing a fractional integral of a nth derivative of a function, the result is not as simple as the previous cases. So previous cases means for the case of an integer. For example, if you have a function f, and if you are doing a derivative of integer order twice, and if you take the operator d to the power minus 2, means if you are integrate it twice again, then you revert back the function a in case of an integer order derivatives or integer order integrations. But in case of the fractional order, the result is not true in general always. So here after this result, if you have a another derivative, integer order derivative of a function, and you are doing a Riemann-Leibniz fractional integral of order minus mu minus n, and this is not like that n and n minus will cancel. The result is actually like this. So apart from this term, some extra function r, it is a function of the variable t and the order nu. So this function is defined over here. It is a polynomial type function, not a polynomial type because it is a t contains the fractional power. Okay, so this type of function is there, and d to the power k, it is the derivative of the function of integer order, and its value at t equal to 0. So this is the first result. And similarly, if you do the reverse case, if you have a fractional integral of order nu, and if you are doing a fractional derivative, the result is also can be reversed. The result can be reversed, but the extra terms are generated, which are again this type of function r. So this is an important result. That result shows that the fractional integration theories are actually a little bit different rather than the integer order theories. And in this result is true only in a particular case when the functional value and its integer order derivatives takes the value 0 at t equal to 0, then we have this simplified results over here. And in case the order of the fractional derivative is greater than n is the natural number, any natural number n. So then you perform this derivative after the over a fractional integral. Then it is equivalent to the fractional integral of order nu minus n times. So now we are going to the next definition, which is called as a fractional derivative. Riemann-Leibniz fractional derivative. Riemann-Leibniz fractional derivative can be defined in terms of Riemann-Leibniz fractional integral d to the power mu of a function ft. It is defined as d to the power m of nu of minus t. So if you case a particular case when mu takes the value integer value, it reverts back to the integer order derivative. So basically, if you observe the definition, there is a twofold definition over here. So first we are doing we are doing a Riemann-Liouville integral of the function. Then we take a mth order integer order derivative over that. This can be represented in a very good manner in this diagram. We have a function ft. First we are doing the m minus alpha order Riemann-Liouville integral. Then we differentiate as an integer order m. Then we get the fractional order derivative of the function d power alpha. So in this picture, I've taken consider some example. If we choose m value is 3 and alpha value is equal to 2.3, then at the initially you have the function, you are over here, you have a f to the power 0, you have the function, original function. This is the first order derivative, second order derivative. This is the first order integral, second order integral. So what we are doing first, we are going back we are going backward first over a Riemann-Liouville integral of order 0.7, and then we are moving to a step length of 3 to get the point 2.3 order fractional derivative at this point. So here these are some examples how we can calculate the fractional derivative of some standard function. Suppose you have the function 2 to the power alpha. So we have already discussed that fractional integral of the 3 to the power lambda function is given by this, and using the d to the power mu, using the d to the power mu t to the power is equal to d power m d to the power minus mu t lambda. So using this definition, this fractional derivative, mu fractional derivative of the function t to the power lambda, it is expressed into this form. One very interesting property to observe from here, that if we set the value of lambda equal to 0, if we set lambda equal to 0, then t equal lambda, you have the function as the 1. It is a constant function. Then if we do the fractional Riemann-Liouville fractional derivative of the constant 1, so it gives the value as 2 to the power minus mu divided by gamma of 1 minus mu, which is not equal to 0 in general. So this gives the first interesting result, that the Riemann-Liouville fractional derivative of a constant function, it is not equal to 0 always. Similarly, if you look into the exponential function, the Riemann-Liouville fractional derivative of exponential function, it is no more the exponential function. This function can be represented as t to the power minus mu in terms of the Mittag-Leibler function of order 1 minus mu of the parameter t. So if you look that, you have a standard knowledge that if you have a function e power t, if you differentiate or integrate it, it remains always the same. If it, how many times, it doesn't matter. So in case of the fractional derivative, the picture is little bit different. So if you have an exponential function, it is no longer after taking a nth order fractional derivative, it is no longer the exponential function, but it comes to a more general function, which is the Mittag-Leibler function. So here it is these are the rules which discuss that how we can interchange the derivative and integral operators in sense of a Riemann-Liouville. So if you have a Riemann-Liouville integral of order q, and then if you are doing a Riemann-Liouville fractional derivative, the resultant is the p minus qth order fractional derivative. But if you interchange the order, the result is little bit different. So the result also says that the interchange of Riemann-Liouville derivative and integrals does not commute always. So if you have a derivative and then integration, after you have integration and derivative, the results are different. These are the result where it says about the commutativity of the Riemann-Liouville fractional derivatives. In case of the fractional derivatives also, they are not commuting to each other. Means that if you are doing a fractional derivative of order p, order q first, and order p then, and if you do reverse the process, the results, this result and this results are totally different. Different in the sense that first term is equivalent, but if you look into the second term is different because it contains the fractional derivative values of order q minus j, and the second one contains the fractional derivative values of order p minus j. So p and q are not same, then these two results are vary. So another conclusion is that the fractional derivatives of Riemann-Liouville, they cannot commute in general, but in some particular cases they can commute. So now we are going to the next kind of definition, which is called as a capital fractional derivative. This capital fractional derivative is basically the another definition of a fractional derivative. So here it is defined in just the reverse order that you have defined in a Riemann-Liouville integral. So it is the notation is this. We are using this C notation to understand that it comes from the capital sense. Capital fractional derivative of order alpha over the interval 0 to t of the function ft. It is defined as 1 by m minus 1 and f to the power m. It is an integer order derivative of the function, and this is the kernel function. So it means that, so in case of the capital derivative, what we are doing the derivative of the function first, and then we are doing the Riemann-Leibniz fractional integral of order m minus alpha. So this can be imagined in this picture. So in case of a Riemann-Leibniz, you have a function ft, then first you are doing a mth order integer derivative, and then you are doing a m minus alpha order fractional integral to get back to the fractional derivative. So here the picture is like this. Suppose we are setting the same value that we have set previous example. So m value is equal to 3 and alpha value is equal to 2.3. We want to find out what is d to the power 2.3 order derivative of function ft. So in this case, first we are moving forward with a length 3 with a third order derivative, then we come revert back to a fractional integral. So if you see that the process over here, it is just the reverse of the process of the Riemann-Leibniz. In Riemann-Leibniz, we have initially go backward and then forward, and in case of the capital, we go forward first and then we go backward in the sense of a fractional integral. But in a particular case, when alpha takes the value alpha, taking the limit as an integer, this fractional order capital derivative, it reverts, it gives the integer order derivative. So the theory is consistent. It is a generalization from the integer order definition. And here are this is the relation between the Riemann-Leibniz and capital. If you can see that these two definitions are just the opposite in the sense of the operator in the two definitions. So, and they can be related. It can be proved by using the integration by parts result. The Riemann-Leibniz fractional derivative of order mu, it is equal to the Riemann capital fractional derivative of order mu plus this some polynomial terms, polynomial-like terms like that. In general, these two derivatives does not give the same result. They differ by these terms. But in general, if the functional value and its derivative value all are 0 at t equal to 0, they give the same result. Fractional derivative of Riemann-Leibniz and capital are the same. Okay. So here the result that you discussed, it is described over here. So in general, if you have an integer order derivative, and after that if you perform a capital order fractional derivative, this result is equivalent to d to the power alpha plus m. But in case of a Riemann-Leibniz, if you have a Riemann-Leibniz derivative of order alpha, and if you do a mth order derivative, the result is same as this. If you look into these two definitions, these two things are in general they are not equal. So they become equal only under the certain condition. In case of the capital, the integer order derivative and the fractional derivative can commute if the functional value and its derivative at t equal to 0 are 0 for s values from n to m. In case of a Riemann-Leibniz operator, the integer order derivative and the fractional order derivatives can commute if the function and its fractional values and this integer derivatives, they are 0 when s takes the value 0 to m. So, but in general, these two integer derivative or a fractional derivative, either in the sense of capital or in the sense of Riemann-Leibniz, in general, that does not commute to each other. So now, like the normal, when you are discussing the normal integer derivative, we have a concept that left derivative and right derivative. So similar type of concept is also there in case of fractional left and right derivative. So suppose you have a current position is at the time t over here, then the fractional derivative of at, it indicates that the left part of the left derivative of t, which is the past of the t, and the functional value depends on the interval a to t, and the fractional derivative into the notation t to b, it is actually called the future of t. It is actually called as a right derivative, and the functional value depends on all the values of t to 0, from t to b, all the values. So like this, so all the definitions over here that we have discussed, they can be also defined in a left derivative and a right derivative manner. So here is the definition of the left and right Riemann-Leibniz fractional integral. So left Riemann-Leibniz fractional integral of order alpha, it is defined as integration a to t of the order alpha, gamma alpha, a to t. This is already we have defined previously. And the right hand derivative is only change is the change in the interval. So instead of from a to t, it is from t to b. That is and change in the kernel function. That the kernel function is adjusted according to the limit. And in case of when alpha, in general, alpha takes the natural values, natural number. So these definitions are revert back to the previous definitions. And similarly, the Riemann-Leibniz fractional derivatives of left hand and right hand are defined in a similar manner. So this is the left hand derivative, and this is the right hand Riemann-Leibniz derivative. And if you have a function t minus a whole to the power beta minus 1, so these are the properties that the left hand and right hand derivative of all the polynomial type functions can be obtained using this formula. It is interesting to observe one is that if we take beta value is equal to 1, so we have the left derivative of 1 and right derivative of 1. So 1 is a constant over here. So Riemann-Leibniz left derivative of 1 is t minus a whole power minus alpha by gamma 1 minus alpha. Right derivative of 1 is equal to b minus t whole to the power minus alpha gamma of 1 minus alpha. Both of them in general they are not equal to 0. Similarly, the left and right capital fractional derivative are also defined, can be defined in this manner. If in case of the value of n as box alpha plus 1, the definitions are revert back to this definition. And these are the relations between the capital and Riemann-Leibniz fractional left capital Riemann-Leibniz fractional derivative and right capital Riemann-Leibniz fractional derivative. So this is the relation for regarding the left derivative. This is the relation regarding the right derivative. In case a particular value of n as box alpha plus 1, these definitions are revert back to this definition. And another thing is that, and in general, if alpha takes the integer values, then left derivative of capital it reverts back to the f to the power nt, nth order derivative, but the right derivative of capital it reverts back to minus 1 whole to the power n into the integer derivative of the noun function ft. So there is another kind of definition of the fractional integral, which is known as a Wheelie fractional integral. Basically, the Wheelie fractional derivative or integral, they are basically defined over the real line. And when the interval is, instead of a finite interval, when the interval is infinite, so they can be defined using the sense of the Wheelie fractional derivative or the fractional integral. So Wheelie first, this is the definition of a Wheelie fractional integral of order mu. So it is defined over the interval t to infinity of the function ft. It is 1 by gamma of mu, and integration is ranging from t to infinity and tau minus t whole to the power mu minus 1 and f tau beta. So real part of the mu is taken as greater than 0, t is greater than 0. And using this Wheelie fractional integral, we can define the Wheelie fractional derivative, which is denoted by the symbol w to the power mu ft. What is this L? L to the power n. This is basically minus 1 whole to the power n of the integer derivative to the power n. So in terms of so this is the definition of the Wheelie fractional derivative in terms of the Wheelie fractional integral. So like this, the left and right derivative can also be defined. So the equation number 1.13, it is the left Wheelie fractional derivative, and equation number 1.14 is the right Wheelie fractional derivative, which is from t to infinity. Left is from minus infinity to t. Means that in case of a Wheelie, if you have a function which is defined throughout the real line, we can define their fractional derivatives and integral in the sense of a Wheelie. So here is some example. That we take the exponential function. So what is the Wheelie fractional integral of the exponential function? So Wheelie fractional integral of order nu of the exponential function e power minus at, it is basically gives as a power minus nu to the power minus at. So it gives back the same integer function. Similarly, instead of exponential function, if we consider a polynomial type function, the Wheelie fractional integral of the polynomial function, it is actually given by gamma lambda plus mu t to the power minus mu divided by gamma of lambda. Which is this definition. These are all these things are calculated using the definition, and the calculation technique is same as the Riemann linearity technique. So till now we have discussed only three different definitions, but they are not the only one. There are many other different kinds of definitions are there for derivatives and integrals as well. So one of these are few Ganward-Lednikov fractional derivative, this fractional derivative, Capito-Fabry-also fractional derivative, Atangana-Valenu, and nowadays the variable order fractional derivatives is emerging. Instead of considering a constant parameter, we are letting the order of the fractional derivative as a variable, and which is called as a variable order fractional derivative, and is called the Jackson fractional derivative or Q derivative. And in another derivative which is related to fractional derivative, which is called as a fractal derivative. This fractal derivative is actually defined over the fractal dimension, which is not a linear type of dimension. So these are the some examples in this table. I have introduced some examples of some fractional Riemann-Leibniz fractional derivatives of the type of the interval 0 to t. The power function has this already we have discussed. Exponential function is no longer the exponential function fractional derivative. It is instead of that it is actually the Mittag-Leibler function. Similarly, the cos hyperbolic function is the Mittag-Leibler function. Sine hyperbolic is the Mittag-Leibler function. The fractional derivative of the logarithmic function, it is defined in terms of log function and the digamma function. This psi function, it is called as a psi function. It is also called as a digamma function. This is defined as gamma dash x by gamma x, ratio of these two functions. Similarly, instead of if you multiply this, so these are the some examples of some other. If you have a Mittag-Leibler function, then only the Mittag-Leibler function has the fractional derivative, which is same as a Mittag-Leibler function, but of some different parameters. Okay, so now we'll discuss some applications of this fractional derivatives and fractional integration. In case of a integer order derivative or integration, if you have a differential equation, the differential equation generally contains the unknown function or the integer order derivatives of the function. This is called as a ordinary differential equation. So like this, here we can also define the fractional ordinary differential equation. A linear fractional order differential equation is defined by this equation. Here we have only considered on a linear case because only for the simplicity of the presentation, and you can see that the yt is the unknown function, and here we have some fractional order derivatives which are involved on the yn function. And these are some initial conditions. If some initial conditions are provided, then it is called as an initial value problem. If some boundary values are provided, it is called as a fractional boundary value problem. So like this, we can generalize all our standard knowledge of on the integer models. We can generalize them into the fractional models. There are several techniques to solve this type of fractional derivatives. They are generally Laplace transformation, Fourier transformation. Many who do not know what is a Laplace transformation. This Laplace transformation, it is a one kind of transformation of the general category, which is called as the integral transform. So if suppose you have a function ft, if the function is piecewise continuous and is of exponential order, the Laplace transformation of the function ft, it is denoted by the fs function. That is the variable t is on the frequency domain. It is converted to the from the time domain from the frequency domain s. So it is denoted by the same. It is a function of a new variable, which is a variable s. So it is defined in terms of the improper integral 0 to infinity ft e power minus st dt. This is the definition of a Laplace transformation of function. This Laplace transform satisfies some very first property. It satisfies the property of linearity, means that if you have a sums, addition or subtraction of function and you take the Laplace transformation, it is same as the if you do the summation on the Laplace transformation. So it is called as a linearity property, and it is the if you have a derivative of a function, the Laplace transformation of a nth order derivative of a function, it is defined by this finite sum s to the power n fs minus s to the power n minus 1 f to the power 0. Then like this it will continue. Similarly, if you have an integration 0 to t f tau d tau, Laplace transformation of that integral is f by s, and the Laplace transformation of convolution of two function, it is the corresponding product of the Laplace transformation of the function. But the convolution of the function ft gt is defined into this form.
Excuse me, sir. Sorry to interrupt you.
Yeah. Sorry. Yeah.
I think you can take maximum 5 minutes more.
Okay. Yeah, within 5 minutes we'll complete. Yeah.
Okay. Thank you, sir.
So then here are some examples that if you have a power type function, the Laplace transformation of it can be defined by gamma 1 plus alpha by s to the power alpha plus 1. And here is the example that the Laplace transformation, what is the Laplace transformation of a mid-Leibler function. So if you have a mid-Leibler function of order this, so the Laplace transformation of the mid-Leibler function multiplied by power function, it will express into this form. So these are this and the Laplace transformation of the fractional Riemann-Leibniz fractional integral of order alpha. It is fs by s to the power alpha, and the for the Riemann-Leibniz fractional derivative and capital fractional derivative, Laplace transformation of them are expressed as just like the previous derivative formula. It is expressed into this form. So basically, the idea is how we are taking one or two examples how to solve this any fractional differential equation, linear order fractional differential equation using the Laplace transformation technique. For example, if you consider this differential example over the interval 0 to t of fractional order of 4 by 3, and into this as a function of t square. And these are the two initial conditions. So they are if we take the first process is first we take the Laplace transformation of them, then this fractional differential equation is converted to a algebraic equation. After that, we are solving after taking the Laplace transformation, the equation is this one, and then if you from this we are solving what is ys, and again taking back the inverse Laplace transformation on both sides. The solution of this fractional differential equation, it is expressed in terms of a 3 times Mittag-Leibler function as it is. So in this case, the derivative we consider here, it is the Riemann-Leibniz fractional derivative. So instead of Riemann-Leibniz fractional derivative, we can consider the capital fractional derivative also. So in case of a capital fractional derivative, if their initial conditions are, if you set the initial conditions are like this, so process is same. We take the Laplace transformation on this, and so we solve the ys function, and after taking the inverse Laplace transformation, the solution of this equation can be expressed in terms of a Mittag-Leibler function. Okay, so these are some basic examples that how we can solve the fractional order or any differential equation. So, but this in the last 30 years, this topic has been emergingly trending, and it has a lot of promising application in different engineering backgrounds also. For example, to control the engineering system, in case of a fractional dynamical system, if you have, we can model them by using the fractional governing equations, and apart from them, many other applications in diffusion phenomena or in case of mechanical and electric circuit problem, we can apply the fractional governing equations to them. It has also great application in bioengineering and biomedical applications, and it has also application in image and signal processing, and it has also application in the non-local transport in the turbulent flow. And presently, I am working in the non-local modeling or fractional type modeling of turbulent flows. I'm only discuss a particular example from this from my research topic over here. So in general, in a turbulent flow, the concentration is generally distributed by the diffusion theory. In the diffusion theory, it is considered as a local theory. So this is the one-dimensional diffusion equation. So it says that the upward diffusion is balanced by the downward settlement. Whenever this exchange of momentum occurs, this occurs only in between two neighboring places. But in case of a turbulent flow, since the flow is very chaotic in nature, so instead of considering the two-layer moment of transform change of momentum, we can consider as a multi-layer exchange of momentum. So here the comes as a non-local model of a turbulent theory. So we have developed this idea how we can introduce the non-local model over a turbulent flow, and we have introduce the fractional diffusion equation into stress fractional diffusion into this form, and using the Laplace transformation technique, we have introduce a general solution of this to our problem. And this is just an example, one example that how this new solution of fractional order is more improving our prediction of the data in case of a river example. So here the dotted line indicates the traditional model, which is called as a local model. There is no fractional model, and the continuous blue lines are indicates the fractional model. So what are the solutions of obtained from the fractional model? So you can check that the fractional model gives the better idea of the data for the sediment concentration in a turbulent flow. So rather than the traditional model. So it gives the idea that how we can go further using this fractional type modeling for the turbulent flow, because the flow is very chaotic in nature. Okay. Apart from this, many other applications are there. So for the time limit, I am escaping all them. So these are the references that I have used in my presentation. Thank you. Thanks to all of you.
Thank you, sir. Thank you so much. I thank Dr. Kundu for giving such a valuable and inspirational presentation. It enlightened our topic, fractional derivative and its application in various fields. I have some queries from the participant side. So may I ask you,
yes,
sir?
Yes. Yes.
Okay. First question is, relation between differentiation and integration by means of fractional calculus. Is it same when n is integer?
No, the result is not same. If you have a n is integer, so the relation of integration is generally considered as the inverse operator of the derivative. But in case of if you take any real number, n is not an integer, then the result is not always true. The fractional derivative of a particular, if you take in a capital sense, the fractional derivative is no longer the inverse of fractional integral, or the fractional integral is no longer considered as in general considered as a inverse of the fractional derivative of it. It is true only for particular cases only, that I have discussed.
Okay, sir. Thank you. So our next question from the audience is, which fractional derivative or integration is more accurate among available definitions?
Yeah, there are actually the accuracy, it depends on in which kind of problem we are applying because there are different kinds of definition, and in case of a physical application perspective, the capital derivative is generally used, because if you recall that I am going to one of the examples over here. This is the example of a fractional derivative where the fractional initial conditions are given into the fractional order. And in the next slide, this is also an example of a fractional derivative where the initial conditions are taken as an integer. If you look that this initial condition y0 means it is a value of y at 0, and it is a first order derivative of the unknown function y at 0. These are the initial conditions. If you look that in case of when you are trying to apply a equation in case of a physical problem always relates to the physical interpretations of the normal derivatives, integer derivatives we have. For example, this first order integer derivative, it defines the velocity. Second order derivative, it defines the acceleration. So it has a physical meaning. Initial conditions has some physical meaning. So in this physical type of problem, we can apply the governing equation or choose the derivative from the capital sense. But if you are not applying in any physical problem, you can set the problems as any arbitrary order. If you look that in these two are also initial conditions, but in these two initial conditions, the initial derivative is taken into the fractional manner. But till now, there is no physical interpretation. What is d to the power 1/3 of a yt function? There is no physical interpretation. So in case of a physical perspective, you have to think upon the initial conditions also, not only the governing equations when you are trying to apply. So in case of that problem, we can apply capital. We can also apply Wheelie fractional derivative, but Riemann-Leibniz fractional derivative is not suggested.
Okay, sir. Sir, once again, thank you so much for your informative session. Now, I request Prakash to continue.
Okay, thank you, Partha. May I now invite my colleague, Mr. Nizamuddin Ahmed, for vote of thanks.
Am I audible to all of you?
Yes.
Yes.
Thank you, Dr. Das. Good afternoon, all. It is an honor for me to express my gratitude to everyone present here on this day. The essence of all beautiful art is gratitude. I, Nizamuddin Ahmed, on behalf of the T.D.B College and the entire organizing team, extend my hearty vote of thanks to all the honorable speakers and who blessed us with their presence and views. We are grateful to Dr. Sudip Samanto, Assistant Professor, Department of Mathematics, Bankura University, for expressing his view on the topic predicting love life of a couple from love affairs model. I must mention our deep sense of appreciation for our alumni, Dr. Subhasis Chatterjee, Professor, Department of Applied Mathematics, ISM Dhanbad, for inspiring us through his speech on soft computing techniques, which is an emerging.
Excuse me. Isnaji sir, please stop your presentation.
Yeah. Okay. Yes.
You can continue.
Soft computing techniques, which is an emerging area of applied mathematics. I would like to extend a special thanks to Dr. Snehasis Kundu, Assistant Professor, Department of Mathematics, NIT Jamshedpur, for expressing his view on the topic fractional derivative and its application in various fields. The way he explained the topic is exemplary. I would like to express my gratitude to our principal sir, Dr. Ashish Kumar De, for providing us encouragement, support, and opportunity to organize this webinar. I would like to express our profound gratitude to our VC sir, Dr. Sadhan Chakraborty, for his support. I would like to thank IQSC coordinator, Dr. Sarbendu Vikas Dhar, for his support and guidance. I would like to thank Seminar Committee Coordinator, Dr. Angona Ghoshal, and all members for their support and guidance. I would like to thank Dr. Shreyasi Gupta, Assistant Professor, Department of Geology, for her special assistance in preparing the flyer of the webinar. I would like to thank Mr. Subhasis Dotto, our technical assistant of the webinar, for all his efforts. I hereby congratulate our convener, Mr. Probir Sen, Assistant Professor, Department of Mathematics, T.D.B College, for this webinar. We have been very fortunate enough to have a team of very dedicated and motivated colleagues, Mr. Probir Sen, Mr. Partho Mondol, Dr. Prakash Das. Thanks to all of you. I am happy to express my hearty thanks to our entire family of T.D.B College for making this webinar a great success. Our heartfelt thanks to all the participants for active participation and making this webinar successful. Thank you so much for your cooperation. Once again, thanks a lot to all, directly and indirectly involved in this program. Thank you very much. Thanks to all of you. Now I request our convener, Mr. Probir Sen, to deliver his end message. From here, I hand over this session to you, sir.
Probir sir, can you hear us? So, Probir sir?
Am I audible?
Yes.
Yes, you are.
Thanks, Nizam. There is an important announcement for our participants. Please fill up the feedback form whose link is provided on the chat box of Google Meet and YouTube Live to get your participation certificate. Feedback form is compulsory for getting an e-certificate. Thank you all for making this webinar successful. We believe that the world must come out of COVID-19 pandemic. So stay home, be safe, take care. And here I conclude this event. Thank you all.
Thank you, everybody.
Thank you, everybody. Thank you.
Thank you.
Thank you.
Thank you.